Hello, everyone. Uh, Welcome to the Engineering with Julia mini. Some people filtering in. This is the second year for this mini, and it's really exciting. We have a good lineup of talks. The first one is from Michael here at Julia Hub, and it's going to talk about dyad. So please go ahead, Michael.
All right. Okay. So I'm assuming everybody can hear me because I can hear myself and I'm quite loud already. So I'll try not to get too animated and yeah, and too loud. So this is some work that I did in conjunction with my colleague Sebastian Makuta Campanu and me, Michael Tiller, and I'll be presenting, but a lot of this is actually the work of Sebastian and his work on the Julia side of the analysis. I did sort of the dyad side here. So we'll be explaining what an analysis is in dyad, but the point here is to be able to allow people to incorporate their own engineering workflows into dyad. So that's kind of the theme here. So a couple words before I dive into the analysis stuff. I just want to provide a little bit of context here. So first, what dyad is. You've probably heard a lot about it at the conference, but just in case you haven't, I'm just going to touch on what dyad is and why we need it. So this is an example of a component model in dyad. And this is actually a DC motor, if for anybody who's interested. So there's an inductor, a resistance, an EMF, and an inertia. And the thing about dyad is that it's a declarative language. It very deliberately has limited expressiveness. It's not an imperative programming language. It's not Turing complete. It's something much smaller than that. And the reason we limit our vocabulary in this way is so that we can actually reason about things. With a much more limited sort of vocabulary, we can actually get further in terms of reasoning about stuff. So we're mostly concerned about engineering reasoning. Does everything have consistent units? And does it make sense to connect a resistor to an inertia? No, the answer is no. Yeah. Things like that. So, but we lean very heavily on Julia in the cases where we need any kind of imperative semantics. And I won't go into too much of that detail, but just understand that dyad is not in any way an alternative to Julia. It's very much a complementary technology to Julia, and it actually compiles down into Julia ultimately. And as I said sort of earlier about the fact that it's declarative, the goal here is to kind of avoid the Turing tar pit. We want to be able to reason about and visualize things nicely. So dyad itself is a way of describing systems that's both graphical and textual at the same time. And as I said, it compiles down to using Julia and the Julia ecosystem like modeling toolkit. And the hope here is to sort of bridge a gap between the engineering world, the people who are sort of in industry building physical things and even building the embedded systems that go along with those physical things, to bridge this gap to the software world or to programming. And I feel it's actually a really interesting example of highlighting and demonstrating the power of Julia, because as I said, it ultimately goes down to Julia. And it's just a way of reaching potentially another community and another market to show the value and power of Julia. So I'm going to just start briefly talking about component extensibility. And then I'll get into why that's important for analyses as well. So this is just to give you a flavor of this. This is an example of a component in dyad. You see the source code on the left. You see just an icon to represent this thing on the right. So one thing to keep in mind about dyad is there are no built-in components. Everything that you use when you use dyad, you could have written yourself. We've saved you the trouble. We've created a bunch of standard libraries and things like that. But you're on a level playing field with us, the maker of the tool. So there's nothing that we're not doing any magic behind the scenes. We're writing in the same language as you would. So you have all the capability and power that we do. And so this is an example of what I would call a foundational component. This is a component that has the mathematical description captured in it. So in this case, in the source code, I'll just walk through some of this. You start off with the connector. In dyad, a connector is a way of describing how two different components might communicate. So in an electrical system, the electrical components communicate via a shared voltage and the exchange of current. And so that's what that thing is telling us. And if we want to define a component, we create a component definition like this. And in there, we first start off by saying how this component is going to communicate with the outside world. So it's going to have a P pin and an N pin. That's how it interacts with the outside world. It also has a parameter R that characterizes its behavior. So this is, a number in this case. You can define variables as well that are just useful in the equations. In this case, you can see here are the relations that exist in there. So I can define what I is, I can define what V is. This is basically just defining a sign convention. And then I can put in two fairly important mathematical relationships. One is the conservation of charge, that any charge that comes into the resistor has an equivalent amount of charge has to go out, and Ohm's law, which hopefully everybody recognizes in here. So this is the way that we can create a reusable physical component model in dyad. Just like you would write a function in a programming language to make it reusable, we are creating a reusable physical component. And then we have up from there, once you've defined a bunch of primitives that capture all of these mathematical relationships that you find in your physics text or your physics and engineering textbooks, uh, now, to me, this is where it actually, I'm still like a kid in a candy store when it comes to this kind of stuff. Because to me, this is where it really gets thrilling, because now you've got these Lego blocks of things, resistors and inductors and inertias and all kinds of stuff, right? And valves and whatnot. And you can actually start building stuff with it. And so then you get into assemblies, which you see here. And so the assembly in this case, again, it's a component model. We don't concern ourselves with what's inside a component. So it might be an assembly, it might be a foundational component. From the outside, it doesn't really matter. It's going to have a set of connectors. So in this case, we have I've left two of them off, but you have things like you have this connector and you have this connector, and then there's two more, it turns out, here as well. That define how it interacts with the outside world. And the outside world doesn't care whether it's equations or whether it's made of other stuff internally. And then you can have child components inside of it, like the resistor and the inductor. You can have parameters, just like we had in the other one. And then you can have connections, which is where you draw these lines between things here. And then we have metadata in the model that actually handles, it retains the information about how the components are laid out, where the wires go and things like that. So that's an assembly. Okay, so I wanted to show the component extensibility first so that you understand that once you have dyad, you have this ability to just create nearly anything, right? It's not that you're stuck with a bunch of, like, it's not like we decide, well, you're going to get resistors and inductors and these things because we think they're important. No, you can put whatever you want into this system. The same issue happens not just with the content in a modeling tool, but it also happens when we talk about the analyses that you might perform, right? Let's say you build this model. What are you going to do with it, right? I mean, you don't build the model just to make a picture and hang it on the wall. You build the model so that you can actually uh, ask it a question. What if? What if I run this as a transient simulation? What's the steady state of this thing? What if I linearize it? What if, right? So there's all these what if questions you want to ask. And again, we don't want to be the people who decide what questions you can ask. We want you to be able to ask whatever questions you want. And so we developed this analysis capability, which is in a way of essentially being able to create a catalog of these kinds of what if questions. So, and this actually, it's worth mentioning, this is all accomplished, again, through Julia. So everybody take a drink for every time I say Julia in this talk. But I want to emphasize that, like, Julia is a super important part of this. Okay, so the doing stuff, the what if stuff. So Dyad has a whole bunch of built-in analyses that you can do. You can do a transient analysis, just let it run in time and see how it responds. You can do a steady state analysis. You can do a linearization. You can do frequency analysis. You can generate an FMU. You can auto-tune a PID controller. You can do model discovery. which are all, I mean, and there's more. I've actually left a bunch off, including sort of some of this, something like what I'm going to talk about in the rest of this presentation. But there's a lot of them that are already there. But again, you're on the same level playing field that we are. We didn't do anything magical to make all these things work. We use the same interfaces that you can use to make your own analyses. Why would you make your own analysis? Well, to my knowledge, nobody, at least internally, has developed like a Monte Carlo analysis, or you might want to do some other, like a design of experiments or some kind of other stochastic analysis. That's up to you. You know, the what if is up to you. So, for example, in medicine, it's very common to want to do population studies. So you want to do some kind of, you know, these kinds of things, statistical analyses and with noise and so on. And so it's not up to us to dictate how you use these models. We want to make it so that you can ask the questions you need to ask. And the one that I'm particularly interested in, because I come from a background in industry and in doing engineering work, is this idea of being able to create custom engineering workflows. The idea being that any particular organization, whether it's a scientific organization or an industrial organization or whatever, they probably have their own processes that they use and their own metrics that they want to compute, and we want to enable you to be able to do that with these models. So you, again, have the same freedom that we do to create analyses. So conceptually, I just want to point this off, right? In conventional tools, they'll have a bunch of built-in things, and you know, you can run those. But if that's not what you need, well, then you have to do something. I don't know what you do exactly, depending on the tool. Um, in our case, Diet puts you in this loop. So what I mean by this is, let me explain again conceptually what's happening. When you build these models in Dyad, you essentially use that to create a symbolic representation of your problem, where all the equations of all these different components are there. There's a representation that includes all of them all the way down for all the components and how they relate to each other. So in most tools, they go straight from the model, which is sort of the graphical thing, all the way to something that's been run, an analysis that's been run. But we stop in the middle. We take the analysis and then we create this symbolic representation. And if you're just using the tool out of the box, you would run a transient analysis, which then picks up that symbolic representation and then creates something you run and gets a result. But the point is, you have the option to just stop at the symbolic analysis and say, okay, I'll take it from here. Oh, okay. I guess I misunderstood something. Okay. Okay. So then I'm going to have to fly through this. Okay. So yeah, start taking questions. Okay. All right. I apologize. I misunderstood the time for this session. So I'm going to show you an example of this. So we can get into this. So this is an example of an engineering system. In here, we can minimize, we have some optimization problem, and we're going to minimize the cost. We're going to satisfy several constraints. And we've written an analysis that does the optimization in this case. And so I mentioned that. Okay, did this. And so if we were to just run our system, we would find that this system saturates our actuator, goes too high, and we want to optimize it so that we get the best fit of this. We're going to try and follow this set point, but it's not saturating our actuator. And I know there are other ways to do this than to just do what we're doing here to limit this. But we then created an optimal control analysis, which I skipped over, unfortunately, to do this. And we run the optimal control analysis. It runs through. You can see all the output from here. And then you see the result. So you see that if we've come up with a controller with a gain that will try to meet our set point as best it can, but not exceed this threshold of trying to drive an actuator harder than this certain level. And yeah, so future work. Yeah, okay, all right. I unfortunately have to stop now because I did not time this right. So if you have any questions, though, let me know. And unfortunately, I didn't get to the meat of what we were going to talk about. But so I apologize for that. And with that, I'll turn it over to our next speaker.
Yeah, it's okay. It's okay. Yeah, you might have time for one question. And is Ronan here? Uh, uh, oh, there you are. Okay. All right. You can start getting set up. Yeah, we can take one question. All right. Well, thanks a lot, Michael. Yeah. All right, our next speaker is Ronan. He's going to be talking about a space mission and the Brazilian National Institute for Space Research. And I think you presented last year too, right? Yeah, yeah. So he's back for another round. Please
Okay,
go ahead, Ronan.
okay, so good morning. It's a pleasure to be here again. Um, I'm here to talk not about a package or something like that, but about a very successful use case of Julia. Uh, for those who do not know me, my name is Ronan Reis. I work with the National Institute for Space Research in Brazil since 2013. My roles in the institute are to be the mission architect and also the technical responsible for the attitude and orbit control subsystems for those missions developed by INPE. Currently, I'm involved in Amazonia 1, Amazonia 1B, two remote sensing satellites in low Earth orbit using cameras. Series 6, which is also a remote sensing satellite but using radar, CO2 image to monitor the CO2 emissions and other gases, and also Sirius 5, which will be a geostationary satellite. Okay, so let's go back a little bit to the past. Amazonia 1 was the project that I started working when I entered INPE. I worked in this project since 2013, and I decided for some reasons to make everything in Julia. The very first version of Julia I downloaded was 0.2. There is nothing to analyze satellites. There is nothing to even print tables. So everything I've done in Julia was to solve a problem I had. That's why I created reference frame rotation. That's why I created satellite to box. Print tables was created just because I needed to print tables, literally, and so on. Amazonia 1 was successfully launched in February 2021 and it's still operational. After 5 years, we can state that the mission was 100% successfully. We see a video here of the satellite being deployed by the launcher. And during this period, I released several packages to analyze satellite-related stuffs. Those are the list. We split into several mini packages, let's say like that. And we use Amazonia 1 as our test bed to validate every algorithm. So after 5 years, we had a lot of data. You see here, it's a little bit small, but the fact is the orange line was what the algorithms predicted. The blue points was what we measured there. So we validated every possible thing using this mission. That's why I call it Amazonia 1 our test bed. You see one image taken from the satellite. Everything is very stable. The image is very sharp. For example, we had this algorithm to compute how much fuel the satellite will use, and we compared to how much fuel it used after the initial phase, and was spot on. I didn't, I'm not lying here. So we go now to Amazonia 1B, which is our successful. Uh, It's also a remote sensing satellite, but with a camera with much higher resolution. Here you can see the satellite being assembled in our laboratory in Brazil. It's scheduled to be launched next year. And in this satellite, we used Julia from the beginning to the end, using those validated algorithms to design the entire mission. I mean, the parts I am responsible with the orbit and the OCS. So for example, in the orbit design, in a very high level, you need to select the nominal orbit. You need to compute what we call the beta angle, which is related to some important things for the thermal analysis. We need to compute the eclipse time, the coverage analysis of our instrument. For the ground station analysis, we need to find when the satellite will access the ground stations. The gaps between the access is important. We need to plot the visibility circles. For the OCS, the attitude, just on parenthesis, attitude is how the satellite is pointing towards something. This is the attitude. So for the OCS, we need to select the actuators, how large will be our reaction wheel, how accurate will be our star tracker. So we need to compute those budgets. We need to turn the control gains. A lot of these projects here, as I presented in past JuliaCon, we need to find the parameters for our filters. One very important thing is the dynamic simulation. We have this very complex simulation that goes from orbit mechanics to the computer clock and algorithm inside the OCS computer. And we also need to perform on orbit calibration when the satellite's launched. We need to align the sensors and the actuator so we can take those sharp images. Another thing we need to do is to compute the fuel budget and also to perform the decay analysis because we need to use the space in a sustainable manner. Everything in blue here that you are seeing are available right now in the satellite toolbox. So you can go download the package and perform the analysis yourself. What is in green is also performed for this mission in Julia, but however, due to intellectual property, was not able to share publicly, but it was, so there is this study case. Julia was used to make this, to compute this. And what is magenta is what we do not have right now, but it was not very important up to now because if you have a very, how can I say, strange sensor with a very strange footprint, you need to compute the coverage analysis to see, for example, am I taking images from the entire Brazil? But for those missions in low Earth orbits with very simple instruments, you can do analytically. So it's not very important, but something I will add to the toolbox very soon. So here's some examples. For example, if you want to design a sun-synchronous orbit, which is the most common orbit in low Earth satellite, you can just run a command. You get all the possible orbits with the important metrics here. You select your orbit and everything is fine. You can do those kind of plots, which is very important because space missions are, you have a lot of people with different backgrounds. Some people do not understand very well orbit mechanics, so it's important to see where the satellite will pass on Earth. Here is a plot where we see the gaps between the communications for this satellite when we leave the visibility circle of this ground station. And then we take all those paths to reach it again in another ground stations. You can do this right now using satellite toolbox. You can compute the beta angle, as I said, the power, the sun radiation power on the solar panels, which is important for the power budget, the eclipse time, how much time the satellite will spend without seeing the sunlight, and some internal things that is important to design orbits. This is the, how can I say, the closed part, right? To the right here, I'm showing to your left. I'm showing the one tool I presented the last JuliaCon, which we use it to include it to how can I say, fine tune the gains of the Amazonian 1B that will be flying next year. Uh, Another thing I want to show here in real time is, oops. So this is how we work. We have this package that use a lot of things, some, of course, closed things here. We uh, add all these configurations regarding our missions, and then we plot those metrics. And this is why I build period tables. I need tables, right? So we have those metrics, those summaries. We check if everything is okay. If it is okay, fine. We design our here is to design the actuators. I just copy this text here, paste on the report, and I'm good to go. We are we did this for all the phases. So I still have. Okay, thank you. I'm almost finished. This is our last edition. It was coded by a colleague called Paulo dos Santos. He worked with me at INPE. It's a very important one. It's the decay analysis. We need to save fuel to perform a last maneuver at the end of the mission. So the satellite can enter within, I think, 25 years. Here we see if we decrease the perigee of the satellite to 500 kilometers, it will enter within 16 years. So we clean the orbit, right? This was our last addition to Satellite to Box. You can just run one command and you have this kind of plot, which is very important. And this is just a bonus because at INPE, I went through different phases of Julia usage. The very first one was why are you using this? You should be relying on Fortran, the legacy. And now, after 5 years, and we've proven that this technology was good, okay, we can do this using any computer language. This is true. I agree. However, I'm pretty sure that Julia provided the shortest path. Not only the language, but the ecosystem itself. And one thing that one guy told me is that all the benchmarks I'm seeing related to Julia are just very simple algorithms, bubble sort, Fibonacci. Uh, I don't think it will work with very complex one. So I take probably the most complex algorithm I had, which was this opt propagator, a very common one. I took the industry standard, let's put it like this way, these Rust and C++ implementation. A lot of softwares embed those algorithms. I took Satellite to Box in Julia and ORCID in Java. You can see that statistically, we are reaching the same level of those compiled languages. Probably if I run these benchmarks again, the rank will just change here. Okay, so conclusions. We are using Julia in all satellite development phases. In my case, for the mission analysis and the OCS design. All the algorithms that we are provided in the satellite to box are validated against a true space mission with excellent accuracy and performance. So thank you very much. I'm happy to accept questions.
Obrigado.
De nada.
Yeah. So yeah, we can entertain a question. All right, here I'm coming. I think, sorry, he's closer.
Um, Thank you for a great presentation. Is there any plans to try to simulate the instruments in Julia or process the instrument data using Julia?
You mean the payload?
Yeah.
Yes. We are looking into it. We have a new equipment in this mission for it's called it takes GPS signal to measure some environment things. We are analyzing if we can use Julia to simulate those. Also, not only the platform, but the payload. But in the platform, we are simulating on all the sensors and all the actuators related to the OCS. For the payload, we are looking into it, but we are not using it right now.
Okay, we have time for another. I'm coming all the way up there.
Thank you. I have one question about you showed a decay chart of the satellite. I wonder what algorithm are you using for the orbital propagation, like SGB4 or SGB8 or some HPOP or something like that?
Actually, this is something very fancy. We use a set of, for example, for the gravity, we use a numerical algorithm, and we take the model from a very used model called EGM08 and propagate it numerically. But we also add, for example, the drag in a but how we add the drag is analytically. So it's a very convoluted algorithm to make this long-term propagation. We are not here. Do not want to know where the satellite will be 2 minutes ahead. We just want to know the overall scenario, how the perigee and the apogee will behave during a set of years. So it's not a true satellite propagation, but it's a long-term satellite propagation, something like that. But the code is free. You can just download it and see. It's very fine. It was a very nice work that Paulo did in Brazil.
Thank you very much, Ronan.
Thank you.
Yeah. All right. Our next speaker is Dimitri. It's going to talk about robots.
Okay. Yeah. Hi, everyone. Thanks for joining me today. I'm Dimitri. And I will going to talk about embedding Julia on this small robots and also embedding it on the Raspberry Pi almost. So I come from Eindhoven University of Technology from the group called Bias Lab. And what we do essentially, we develop mathematical methods, software, and applications for autonomous systems. And we try to do it in Bayesian way. And pretty much everything what we do is in Julia. So we do research, we write software, and Julia is really like a backbone for us. And we have also an open source ecosystem of packages called Reactive Base. And one of our main packages is RX Infer. And then one day we had this small robot in our lab, and I just wanted to help my colleague to play with it a bit. And it's like a really small robot. I will have a picture later. And unfortunately, there was no native Julia interface for that, right? So there was like a Python library, a C++ library. And you may ask, okay, yeah, so what's the problem, right? We have pycall.jl, just call Python and be done with that. And actually, that's what we exactly did. But the problem is, of course, latency, right? So Python calls C++, C++ calls C, C calls like whatever. And it just basically was the problem. And then I looked at the documentation for these robots, and they have a really nice documentation about what they actually do, how they communicate with these robots. And it turned out that it's a very simple binary serial protocol, nicely documented. Yeah, you basically just send raw bytes back and forth, and that's it. And so maybe a question for you: how do you think how hard it is to do it in Julia? Right? Yeah, the answer is like super simple. It's super mega simple to do, really no brainer. And yeah, this is what we wrote essentially in our lab, like a small library for these robots called Ptoy Beetle as a name of those robots. And it allows you to connect to these robots, find actually it on your USB, do some kind of high level commands, stretch, walk, because they're pre-programmed inside these robots, but you can also do some low level commands like, okay, move this particular joint with this particular ID to this angle. And you can play around with that. And there are other commands. I will go over them a bit later. And it's just on GitHub, right? And it's also officially acknowledged by the company. We had like a nice chat with them on email and on Reddit. They really liked it. You can just download it from official Julia registry. Um, so, and the whole library, of course, because the problem was the latency, right? And it has been designed with full performance in mind. So all the communication buffers are pre-allocated. All the commands are non-allocating. It's like pretty much zero overhead. And Julia was really nice because it can, if you know what you are doing and if you like do everything type stable, it is able to compile out pretty much everything and boils down to just sending raw bytes over the serial port. And the library, again, it has like low-level commands to move joins or like some utility functions to scan for ports, some high-level commands. You can also query gyroscope if you have it connected to the robot, etc. And some fun commands like playing melodies. Because this robot's originally is like for kids, so they're small and quite cheap. So it's also a very nice way to maybe buy it as a present for your children, and yeah, just let them play with that and let them learn this. Um, and it was basically like a side project. As I said, I want to help my colleague, and I designed this the core that yeah, for full performance. But then I was like, okay, I don't have time anymore. Just C++, Python API, the whole documentation, give it to Claude, just hammer it in one shot, and it's pretty much done. So yeah, and it works like great. Actually, it's also was a very good time saver for that. And yeah, you might think, okay, so we solved everything, right? It's like, yeah, that was the problem, or the right question is like, was it the problem actually, the latency? Because the next thing that was actually to deploy it on Raspberry Pi to the embedded system. And you might think that this icon on the left is Raspberry Pi icon, but it's actually like a gripe icon because it was surprisingly extremely hard to do. And we already had like this keynote about the compiler, how a compiler gets greater and greater. But for me personally, one thing that I really miss is cross compilation. So it's like super mega hard to do. It's a huge pain and is actually an unsolved bottleneck for me personally, right? So Julia unfortunately doesn't have this native cross compilation, and for Raspberry Pi specifically, it's a big problem because if you want to compile on Raspberry Pi and if you have like a very cheap one, you probably don't have a lot of memory. And and LLVM is like very memory hungry. So you don't really want to do that on Raspberry Pi. And even if you do, it's like super slow and typically runs out of memory. And JuliaC was not stable enough for my purposes. I really couldn't make it work because of some random segmentation fault. So it's still maybe I did something wrong, but the entire process is not very well documented, right? So I would really like to have some kind of a tutorial to see if I am doing something wrong, or maybe it's just not ready yet. And ultimately, it was like not very mature and super hard to do. And actually, like luckily, I asked someone on Slack that Slack is super useful, right? And they said like, yeah, of course you can do this. There's this um, package with this commit, in this folder. There's this SR script that actually tells you how to do this. Like, oh, okay, nice, yeah, good, thank you. That actually helped. So apparently there is a way to do that. So if you're super lucky like me, you can try to precompile something on macOS for Raspberry Pi, and surprisingly, it works until it doesn't. So I will not go into much details how to do that because maybe a month later there will be a proper tutorial. Um, but for these purposes, I just give you a hint that there is a way to do it on macOS for Raspberry Pi specifically. Uh, but okay, I'm done with complaining. So I actually managed to do that at the end, not as far as I wanted, but here is the example where I connect bit-by-bit communication library RxInfer on Raspberry Pi to basically do a state estimation with gyroscopes, so to estimate the orientation of this robot. And the gyro was also super cheap. It like drifts away. If you do it naively, it just flies into the space pretty much immediately. But you can, with RxInfer, I was able to run a probabilistic model and basically estimate this drift in real time, adjust for it, and do a nice state estimation with uncertainty in real time with all of these tools around. And yes, this is pretty much it. Thank you again. So please check out the library, check out our work with RxInfer, and find me on my website and connect on LinkedIn. Yeah, thank you.
Thank you, Dimitri. Here's a question from Rona.
I think for the presentation, I have just one comment, one question. I tried to do this cross compilation to by zero. The only thing that I could do consistently was to use a key to emulate,
Yeah,
let it run
Yeah.
like 2 days
Yeah.
and generate a system image and
Yeah.
then copy to the Raspberry. Was the only thing I could.
I also talked already during JuliaCon to someone else. I also got this comment that I can try. But again, for me, it was just a hobby project, side thing. And I thought it just took a bit too much of my time. So But if I would invest into like different solutions, I'm all sure that there is something else that I missed indeed.
Perfect. And my question is, when I try to embed something that has Raspberry Pi running Julia, I got many problems with the garbage collection. It was very fine, and then after like 8 hours, we saw some strange thing happen. How do you manage to correct this?
Exactly, I definitely agree. Garbage collection is also sort of like an unresolved bottleneck. And the reason for this library also specifically was garbage collection latencies, extra latencies. So the whole communication library is non-allocating because dealing with garbage collection and embedded system is super hard. But if you use some other algorithm, you still have the problem of garbage collection. Like with Ericsson Fur, let's say it still allocates and there are still delays because of that.
Thank you very much.
Yeah.
Any other questions? All right. Well, thank you.
Thank you.
Thank you very much.
Yeah.
Yeah. We'll start in about 4 minutes.
Be careful of bears.
Here we go. Yeah, so our next presenter is going to talk about. So we've had robots in the last presentation. Now we're going to talk about lasers. Petru, please go ahead.
Okay, so my name is Vlad. I am from Romania. I work at the National Institute of Laser Plasma and Radiation in the Center for Advanced Technologies with Lasers. And in particular, my work group is a laboratory that does material science. So what you can see in the pictures on the bottom corner is like the typical setup. We have a robot arm and we have high power industrial lasers. And more or less our task or an important part of our job is to transfer technologies to various enterprises, medium or small or even large. Right, so how this looks in our laboratory is that we mainly have material engineers and they'll come up with an idea, they would do some programming for the robot that would eventually result in an experiment. Then you have to perform some metallographic analysis. I'm not sure if you, the audience, is familiar with this, but like the process of performing the analysis is very painful. After you run an experiment, which maybe lasts a few minutes, maybe an hour, then you have to take the sample and cut it transversely. But you have to make sure that you don't hit it too much from the disk, especially if you have a hard metal. The action of the disk can disturb the phases, and then you lose the information that you're trying to find in the first place. So performing analysis on samples is extremely expensive, and only after we know what happened can we maybe adjust our parameters. So this is a very slow workflow, and it's quite labor intensive. So ideally, we'd like to avoid that. The prototypical case, because we do a lot of like testing the samples to try to optimize process parameters, is to like take a bulk, of the metal, and to irradiate it. So you have some metal, you will irradiate it with a laser beam. The problem is pretty much the heat problem, because while though the physics is a two-way street between everything else, so like stress, hardening, phase changes, it tends to be that temperature is the much wider part of the street, and the way the interaction works the other way around is much like bikes. So like on the other side you have buses, on one side you have bikes. So the PDE is the usual heat equations. This was much discussed in the PDA mini symposium yesterday. And the kind of boundary conditions we're interested in is sometimes Dirichlet, and sometimes they are physical. I call them Rabin plus, because they're like Rabin conditions plus that you have that radiation time, which is nonlinear. So why I chose Julian Ferrite? There are many software stacks. Some of them are very good for this, but for us it's kind of difficult because we're a public institute, we are publicly funded, so it's kind of hard to get constant subscriptions. It's a question about getting perpetual licenses, and those can be expensive. But anyway, Julia is extremely expressive, extremely powerful, and you can get stuff running very easily. I'm by training a theoretical physicist. What I liked very much about Julia is that if I write my equations, I can use all the symbols that you can find in LaTeX. So that was nice for me. And also that they have an active development like package Ferrite, which can help you to write whatever you need, and you only need to focus on modeling the physics. Right, so you have the strong formulations, and then you have the Dirichlet conditions or the Robin conditions, as I said earlier. You go through the variational formulation, and the gist of this is that if you have Dirichlet condition, is because we've recorded an experiment and we want access to information that we could not get otherwise. So if we're interested in the temperature inside the volume of the sample, then there's virtually no way to get information at every point. You could maybe drill a hole to put a small thermocouple inside, but that's like tedious, difficult, and even so you can sample a few points, not everywhere. The other side, where you use the physical boundary conditions, then that is where you can get people out of the lab. So if we get good agreement between results and experiment, the simulation result and experiment, then maybe we can get people out of the lab. And given how long this process of analysis can take, the FEM simulation doesn't have to be the most performant thing ever, although we'd like so, because we often try to optimize the process. Right. So as you might well know, I'm more of a user. I'm not exactly a developer. I'm trying to still wrap my head around how this package ferrite works and how to use it together with differential equations packages to try to get good performance. But the idea is that it discretizes to either a very simple system on the left or a more complex system on the right. Okay, so for starters, the right side term, if you ignore radiation, admits an analytic solution. So this is what I've been doing before trying to implement them. But the problem with the analytic solution is that it's dependent on the domain. So if you don't have a regular domain, you cannot write the analytic solution. Right, so in order to discretize the equations, you just like use ferrite, you ask, please assemble in a loop. I think this is like straight out from the documentation. It's decently fast, definitely faster than anything I can write. And then with these components assembled, you can switch to differential equations. Uh, I've been trying to see if updating the boundary conditions at the step limiter is better or worse. You can choose to update the right-hand side time a term live, but the difference is obvious. But the issue for us is that if we don't have the sensitivity in the machine to measure, maybe the difference is not so bad. And if we can get some extra performance from extra speed up, we don't mind. All right, so dealing with the nonlinearity, basically, you can just go ahead and treat it as is. The problem is that the Jacobian will no longer be a constant. You can do this linearization trick where you use the previous step for t to the third power and everything else is actual, and then you will have a constant Jacobian. But the problem is that we won't have a constant Jacobian anyways, because in reality, when you're dealing with metals at these temperatures where the energy is very concentrated in a small point. You can reach points with 1000 degrees Celsius, 2000 degrees Celsius, depending on the material. And everywhere else is much, much cooler, like 200 degrees Celsius. So you cannot ignore the variation of parameters with respect to temperature. So what I've tried to do is that there are these potential transformations, and I've tried to linearize, or rather say, make the matrices constant to try and save up some computation time. It turns out that at least for this problem and for the combination of solvers I've been using, you don't gain much. The solver dominates much more than the assembly. But anyway, it works. And how do I know it works? We ran an experiment. There's a whole side quest here where I took the thermal cameras and I had to write some software to invert the basically the proprietary codec to get some thermal information, right? So there's a lot of tricks behind this scenes, trying to map the emissivity, because emissivity changes once the surface is irradiated, right? So we ran it against the experiment, and it's a pretty good agreement. And just to be sure, I ran it again. So yes, I ran it again. It's pretty much the same setup. The only difference is that it was a bit later, and the temperatures are quite a bit different. So like there's like a 5-degree difference in the thermocouple evolutions, right? But the simulation works with both pretty decently, right? So why do we want to know the temperature? So as I said before, pretty much all interesting properties of materials can be written in a way that's downstream from temperature evolution. So this is a kinematic model, meaning that you can write the phases, the transformation of phases in the material as a function of the history of the temperature. So you can forget about this. What matters is that the hardness at different points in the material can be written as a function of the history of the temperature, right? So because you have the physics exposed, you can write a simple implementation. And once you have a simple implementation, then you just go ask for callbacks, and at every accepted time step, you can evolve the phases. If you evolve the phases, then you can write the total hardness as a sum of the fraction of the phases of the each contributing phases hardness, right? So also because I'm working with engineers, they have a lot of CAD. This is just like a very rough implementation of me trying to import some meshes I got from them in Ferrite GMesh, which is another reason why, as a user, I was interested in Ferrite in particular, because it seems that the ecosystem is very lively. There are visualization packages and a lot of other useful stuff that can make developing easier and putting something together in a short span of time. Right, so I ran some quick simulations to see if this works, and it kind of does, but it still needs to be validated against some experimental measurements. So this is more or less my talk. Uh, uh, if you have questions.
Thank you. Are there any questions? All right, I'm coming up. No, we're supposed to use the microphone. That's all right. I'm getting my exercise.
Excellent talk. Thank you very much.
Thank you.
I might have missed it. I was wondering, could you say something about the computational time of that simulation that you showed and the scale, if you could remind me of that?
Which one?
I think, whoops, where you showed the thermoevolution, or was that a measurement? Was this a measurement or the simulation?
This
itself?
one?
Yeah.
No, so the trick here is that we had an experiment, so we have the exact block, more or less. I took the parameter data from literature, right? So I made the way the properties vary in time, and I ran the simulation using Dirichlet conditions driven by a thermal camera, right? So this runs very fast. I don't remember exactly the runtime. We can look together later if you want. I think something like 3 hours, 4 hours. Because there's this kind of a funny consequence of the heat equation, because in lasers you have very concentrated heat energy. What happens is that this concentration would be described in Fourier terms with very high spatial frequency, but those decay very fast. And since the hotspot moves a lot, it pretty much doesn't matter. More or less like the cool field, so let's say stuff that's below 300 degrees Celsius matters far more than the temperature when you have Dirichlet conditions. When you have a surface source or a volume source, then the physics of radiation and everything around it is much more complicated, and you want adaptive meshing perhaps, and I've seen that's just been added to ferrite, so another reason to use it.
And the scale of this, is this like a 5 by 5 square roughly, or what I'm looking at?
So like the dimensions, the physical dimensions are like, I think 100 millimeters, 100 millimeters, and 10 millimeters in height.
Okay, great. Thank you very much.
Thank you.
Any other questions? Anything else? All right. Thank you, Petro.
Thank you.
We're looking for the next speaker. We can try to find it for you. All right, Humberto, just take it away.
Lovely. Good morning. Thank you for being here. And I believe the timing coincides with your coffee break. So I appreciate making the space to stay here. So my name is Humberto Medina. I'm an associate professor at the University of Nottingham. I am part of the Mechanical Aerospace Systems Group. Um, some of the people that have worked on Excalibur. So I have my colleagues on the top, and of course, all the people that have contributed. So many thanks to them. I'm going to name some of them because part of what I want to tell you today is not only what we have done with this package, but also how easy it is to take advantage of Julia and making the workflow for CFD nice and easy. So if you are not familiar with what CFD is, this would be the poster child. You have a tool that you can use to evaluate what the aerodynamics, thermals, or essentially it's a design tool. The reality is not that beautiful when we are working with our partners, for example, Rolls-Royce or Airbus. This is the sort of engineering products we have to deal with. So in my group, we do a lot of work on gas turbines, specifically looking at lubrication, transmissions. But you might have simulations where you're trying to optimize a combustor, for example, as very complicated multi-physics problems. And earlier, the previous speaker was talking about laser simulations, and this is an area that we're actually going to start next year. So we're looking to extend the capabilities of the software to facilitate some multi-physics simulations. So I'll try to find you later and have a chat. So we took inspiration from the Joule idea. So if you had the two-language problem, you want high productivity, dynamism, but you also want fast code, right? So that's where Julia started. And we thought, well, why not apply the very same idea to CFD? Our problem is on the workflow. You have complicated physics. You have maybe problems that don't have a off-the-shelf solution. So you would like to have your researchers, your PhD students iterate quickly, but we also want to be greedy. We don't want to have to port that to packages like OpenFOAM, where the time that it takes to sort of break even and start being productive in the language can be a barrier. So can we have both? And this is a quick schematic of what that the idea is. You have Excalibur providing essentially two interfaces. One interface for development. This is where our researchers are working on. That is intuitive, nice, dynamic, and you also have an application API, so you can use CFD. What is very nice is that we're also take advantage of the Julia ecosystem. Being a Julia package, Excalibur.jl is very composable, so we can take advantage of machine learning libraries, optimization, and whatnot. We don't live in an isolated world, and the Julia ecosystem specifically for simulation is growing rapidly, and there's amazing packages out there. And I thought I will name some of the better known ones. You have Trixie, Oceananigans, Water Lily. Essentially, Excalibur is not competing here. It's just found a nice little area where we can contribute to the community with a finite volume method, general purpose CFD code. I'm not going to go through this in a lot of detail, but I think what I want to tell you is, well, it started about the pandemic. You're looking for some ways to kill time, and I discovered Julia at the time, ported a 1D finite volume code that I had in MATLAB, nice and easy. I go, I like this language. So it became a pet project, and in fact, initially it was called FVM 1D, but very quickly became a 2D code, put it in GitHub in 2023. And I thought, well, actually, it's ready to maybe see what the students can do with this. And you can see that by version 3, I wonder if I can, well, you can. So version 3, we now have the first student contributors. So these are MEng aerospace students. Contributing things like the XPU Foundation using kernel abstractions. You have Oscar, who did the UNV parser. So for the first time, we're actually able to do 3D simulations. And Tim Ward, who did some of the composability test. And I'll show you that as an example later. Each feature brings new functionality. So by version 0.3, we had RANS modeling, LES modeling. For the sake of time, I'll just move on and tell you that now we have a lot more of the students are contributing. On version 0.6, we have multi-phase, multiple reference frame functionalities, thin film models. One of our PhD students has added some runtime post-processing capability for turbulence statistics extraction at runtime. And the first contribution from Claude. So our density-based solver was use Claude for that. So that was actually quite fun. We are able to do this because the Julia ecosystem already offers a lot of that foundation you have for parallelism, kernel abstractions, atomics, accelerated kernels. The GPU ecosystem is pretty strong. I think Tim is doing a great job with CUDA. But you also have packages like Adapt that allow you to move data structures across. We also have very strong linear solver libraries there. Excalibur in particular is using Krylov.jl. But again, you have also things like static arrays, allows you to express your 3D geometries in pure vector notation. Great, you don't move away from the math notation, so that's quite handy. So what Excalibur offers is a nice DSL, essentially using some of the nice Julia multiple dispatch to create this representation of a PDE. And we feed that to our solvers, and that's essentially that internal developer API. So I suppose the point in this slide was to just show that, yes, it makes the whole development process easier, so our students are able to contribute directly to the code. And this is what we get. So we're a couple of years old, and we now have incompressible capabilities, compressible flow, multi-phase flow, transient, steady. So it now is in a position where I was happy to come here and say, well, this thing has the general user-facing API in a pretty stable condition. So please try it and let us know, give us your feedback. I did promise, this is an example from Team Word, and essentially what you're seeing here is a very simple example. You have an airfoil, we're trying to optimize it for the best lift to drag ratio, and the red dot is the experiment, and the black dots are the experiment, the red dot is the optimization answer, pretty close. So it's a simple case, but it does demonstrate that all we need to do, you can see that red line arrow, all we need to do is pass the Excalibur simulation as a function to this other package that exists in the Julia ecosystem, and it works. As simple as that. So this is a nice time where I can go here very quickly, show you what the first API looks like. So this is the application user level API. I'm not going to go through all the details here. This is nicely documented in our website. We are ex-OpenFOAM users, so we take a lot of inspiration for OpenFOAM. We don't want to say we want to replace it. It's got 30 years worth of capability. But if you're building something new, it is quite easy and it's quite enjoyable to work with this package in Julia. So you define boundary conditions, you have your setup. Eventually, you pass a physics model to your run simulation, and you're ready to go. So I'm going to be crazy here. I'm going to try and run this in the time I have. This is how quick I think this is going to be. And I'll continue. Performance-wise, it's doing great, especially if you have a workflow where you're sitting on a workstation. It is hard to find something better at the minute. OpenFOAM on the CPU still has better linear algebra, but we're getting there. Unfortunately, this benchmark plot is from the previous version 0.6. I haven't been able to run it, but we're about 1.5 times faster now than OpenFOAM on the CPU. Now, when it comes to the GPU, this is on a 2060, so this is a pretty crappy old GPU these days, and you're still getting a 1620x speed up on these simulations. Benchmarking, please take it with a pinch of salt. It's very difficult normally. When you're looking at CFD codes, it's even more complicated. You have to think about how does the linear algebra work in the back? How does the tolerances are defined? So One thing that we do want to do is include the coverage that we have on the benchmark so we can have proper comparisons. And I think it would be nice to use the Spuma project as a benchmark on CFD acceleration in CFD. I'm going to go quickly through this. How are we using it? We're using it for looking at new fuels in aerospace, so hydrogen fuel simulations. We are interested in multi-phase flows for transmissions. We're interested in fundamental flows, looking at turbulence and transition modeling. These are projects that we have live that are using now Excalibur to give us some real scientific engineering data. Where are we going next? We are, I would call it node bound. We can work in the cluster in a single node. We are multi-threaded. We have single GPU coverage. Where we're going next, and you can see here is a bit of a roadmap. It's not including everything, but now we have a prototype for multi-GPU and sort of massive parallelism. Hopefully that will come live in the next year or so. We have a brand new AMG solver to speed up the Poisson equation, which is a bottleneck that we have in a lot of the simulations. And again, for the sake of time, I'll not run through the entire list. I think the point is, please give it a go. Tell us any pain points that you've had. And if you're interested in contributing, we're always welcome to PRs, or if you want to have a collaboration, have a chat, please do speak to me later. Let's see if this is working. The first thing is, so this is of course, you do this in there and it runs in less than 3 minutes. You do it live and it doesn't run. Hopefully I have a previous result. I'm trying to see what I did. So you have to take my word, this runs in about 3 minutes. I wonder if I change my power settings in the... But thankfully I have one pre-stored result that I'll show you very quickly. So I ran this simulation in there earlier, took 2 minutes and 45 seconds. And it's a complicated, complex engineering configuration. Typical live demos. Do you have any questions?
Thank you very much, Umberto.
Congrats on that.
Sorry.
One great thing in OpenFOAM is that you can define the units of everything and it checks and does a sandwich check on your equations. Do you do something similar?
In my long list of features that we want to add, we want to put in units. I'm thinking of bringing in support for unitful. It seems that it just makes sense. So.
Any other? Oh, yeah, sure.
Can you elaborate on which benchmarks you compared your code with OpenFOAM?
So this one is one of our own, is a 500,000 backward-facing step case. We are where we need to bring in some more rigorous benchmarking.
Is it 2D or is it 3D?
3D.
3D. Okay.
So that's a 3D unstructured full tetrahedral grid.
But is it a RAND simulation or LES?
This one's runs.
Runs. Okay. Yeah. Okay. I might. Okay. Thank you.
Any other questions?
Oh, it is. So it took a little longer, by the way, that it runs for me. So it's 4 minutes, not the 2.45 that I promised.
That's okay. Thank you very much, Umberto.
Thank you.
Our next speaker is Sebastian. He's going to be talking about thermodynamics. Thanks again. Yeah, thank you. No, it's great.
All right, welcome to my talk. I'm going to talk about ML thermal properties, which is a package for hybrid models for thermodynamic property prediction in Julia. My name is Sebastian Schmidt, and I'm working at the Laboratory of Engineering Thermodynamics in Kaiserslautern. So what are thermodynamic properties? So thermodynamic properties are a description of how molecules behave. For example, we want to describe how the relation between the density, the temperature, and the pressure, or we want to know when a mixture starts to boil. And where do we need this information or information about thermodynamic properties? For example, in chemical industry, energy, life sciences, or lubrication. And in all of these fields, we need thermodynamic properties to design processes or machines or to even develop new materials. I'm going to focus on chemical industry. And as an example, in chemical industry, we always have raw materials that we want to transform to products. And usually we do this in two steps. First, we have a chemical transformation, so we have reactions where our raw materials react. And usually we don't get our product directly. We get a mixture of different substances where we need a second step to separate our products. So we need a purification. And in the end, we have our product. And to design those processes, we need information about the thermodynamic properties of these mixtures. And now we could ask, why do we need prediction? We could just measure all of these properties. So this becomes clearer when we look at the number of technically relevant mixtures and pure components. So we have around 120,000 technically relevant pure chemical components. And theoretically, we could build around 7 billion binary mixtures out of these pure components, and even more ternary mixtures. And then we need to know the properties of these mixtures at different state points, for example, different temperatures or different pressures. And we need to predict different properties. So this is a combinatorial explosion, and we cannot measure every mixture and every property here. So predictive models are crucial here. Luckily in Julia, we have Clapeyron. Clapeyron is a very rich thermodynamic library for thermodynamic property prediction written by Andres Friedemann and Pierre Walker and others. And Clapeyron already has some model classes. The two main model classes are activity models, which are used to describe mixture properties based on the Gibbs excess energy, which is GE. And we have equations of states, which describe the full thermodynamic behavior of a fluid based on the Helmholtz energy A. Besides the models that are implemented in Clapeyron, we have a lot of thermodynamic solvers. And the problem is now we don't have parameters for all of these different mixtures we want to model. So what we did is we developed hybrid thermodynamic models and implemented them in the Julia package mlthermoproperties.jl. So what are hybrid thermodynamic models? We use a data-driven approach and combine it with hard physical constraints. So we enforce the physical constraints either by the architecture or we predict parameters for existing physical thermodynamic models. And one example here is a hybrid model for the Gibbs excess energy, which is called HANA. And here we use the fact that we can describe the Gibbs excess energy and then use the thermodynamic solvers from Clapeyron. And HANA works as follows. So we start with the SMILES representations of the molecules, which is a string representation available for every component. Then we use a language model to get a chemical embedding, and then we learn pure component and mixture representations. And in the end, we apply thermodynamic constraints, and we get the Gibbs excess energy as a learned property. So we can use it to describe mixture properties. Another and here we can see how this works. So we use the activity coefficients gamma I to describe a vapor-liquid equilibria here in the middle. And here we have a vapor phase in equilibrium with a liquid phase at a given temperature and pressure, T and P. And this is plotted here on the right as a temperature over mole fraction diagram. And this dotted line here connects 2 points who are in equilibrium. And as you can see, we have different concentrations in the gas and in the liquid phase. And this fact can be used for separation processes, for example, for distillation. Another example is a hybrid equation of states. Again, here's only the smiles is required of the component, and we describe the Helmholtz energy of ideal gases. And this is trained to ab initio quantum mechanical data and can be used as a building block of a general equation of state. In ML thermoproperties.jl, we have a lot more models implemented. HANA and modified unifac are activity coefficient models. Kappa is a vapor pressure model. EASE is a model for diffusion coefficients. And we already saw the hybrid EUS. All models are pure Julia implementations and are compatible with the Clapeyron solvers. And besides the thermodynamic models, we also have an implementation of chemical foundation models like Camberta or SMETAD, which are available through the subpackage camberta.jl. Now I want to show some examples. Here we used the HANA model together with the Krapper model to describe a vapor-liquid equilibrium of the system ethanol and benzene. And the result is shown here on the left. And as you can see, we agree very well with experimental data. And the azeotropic point here is only predicted based on the smiles. Then another example for ideal properties. So here we have the ideal gas property of 1,3-dioxypane from the ideal gas model and compare it to the quantum mechanical calculations. And as you can see here, we have a very good agreement with the quantum mechanical data over the whole temperature range for the Helmholtz energy, the entropy, and here for the heat capacity. And for the heat capacity, we also compare to experimental data, and here we also see very good agreement. Now I showed how we can calculate thermodynamic properties, but the big advantage of a Julia package is that we can integrate it into the whole Julia ecosystem, and this was done here. So here we simulated a batch distillation shown here on the right. So batch distillation is an instationary process where we start with filling up the reboiler vessel with a liquid and then heat the liquid up until it starts to boil, and then we can see or we can observe the concentration over time, how it changes. And here we modeled this batch distillation with modeling toolkit, differential equations, Clapeyron, and ML thermoproperties. So we used ML thermoproperties to describe the vapor-liquid equilibrium of the system. And the good thing is we have a lab where we have such a batch distillation apparatus, and we compare the results of this simulation to real experimental data from our lab. And this is how the results look like. We see here the concentration or the mole fractions of all three components as a function of time. here in the reboiler vessel and at the top in the buffer vessel. And as you can see, we agree here very well with the experimental data. So the conclusions and a short outlook. So we have implemented hybrid thermodynamic models in MLThermalProperties.jl, which combine a physical structure with machine learning in pure Julia, and we only need the smiles for predictions. We are fully integrated with Clapeyron.jl and composable with the Julia ecosystem. So in the future, we will develop new models to predict more properties, and we want to apply the models in ML thermal properties to optimize formulations, for example, refrigerant optimization in heat pumps, or the chemical process optimization as we saw in the last slide. So thank you for your attention, and I'm happy to answer questions.
Thank you, Sebastian. Are there any questions? All right, so if the next speaker is here, you can come down and get set up with the microphone.
First of all, thank you for a really nice talk. I have a question regarding the thermodynamics and how you enforce them. Do you apply hard constraints or soft constraints in the model that you're using?
We have hard constraint the model. So there are two types of hard constraints in physical or in hybrid models. We can either embed or predict parameters of an existing physical model, which is consistent, or we constrain the architecture of the model. So, and both of these approaches are applied in those models, but the constraints are hard, so they obey physical laws.
All right, thanks.
Any other questions?
Thank you for a very, very nice talk. And I'm interested in the, do you have any plan to treat solid phase?
So
I am interested in the sulfurs,
yeah.
solid phase. That problem is very similar.
There are some solid solvers in Clapeyron, mainly for solid liquid equilibria. And one of my colleagues is working on a model that also supports solid liquid equilibria. So this might come also soon, or might be possible soon with the ML thermal properties package.
All right, any other questions? All right, well, thank you very much. Please go ahead, Martin.
Thank you very much. Just out of curiosity, are there any civil engineers in this room? Oh, okay, more than expected. Okay. Hi, everyone. My name is Martin, and I want to show you our project which we are coming up with. And you're now currently in the civil engineering domain, so welcome. And in this domain, you are now in the niche of railway engineering. And we are quite responsible for all the railway infrastructure you're seeing out there, at least our domain, not me personally. And I want to talk to you about the state of our idea, the Rail Toolkit, and how we want to foster the Julia ecosystem for our railway research. And this is an idea I come up with my colleague, Gregor, but it's in an early stage. And I want to show you how we built it around as a package, which I created with another colleague, Max. But let's go. So in the domain, we have quite a lot of computational needs for our engineering and research stuff. And we have quite a lot of tools out there for this computation, but they are all basically data silos. So we have quite a lot of closed tools. We had quite a lot of open tools, but they don't really interact currently. So there's the good, the bad, and the ugly. And what we actually need is something that we can build up to on our open science stack so that we actually can share our data, our environments, our ideas, and what we actually want to aim for. So this might sound familiar to you if you are into open science and all the things, but we need to change the thing also in the railway domain, which is currently quite closed, unfortunately. So the main idea is that we want to have a shared community and a shared computational foundation with you. We have 3 columns for that, and this is basically the pitch, so that everyone who is interested might come to us and talk to us so that we can build together the foundation and the place where we can meet and improve the science stacks together. We have design rules. So the design rules are based on the state-of-the-art research software engineering research. So the main concept of that is that PhD students move on when they finish their project after they're getting the degree. So we have to build an environment where people can actually move in and out. So to do this and make the tools last, which the PhD students are building, we need to make the core concept that people rotate in there. So we need these design rules to have our values, which we want to transport with the Rail Toolkit at place. So we want to show our work, we want to share it openly, we want to check it against real stuff. So for instance, if you have this rail join here, this could be a reference. This is also a reference to how that we need clear interfaces to patch together different packages we want to create, and we want to create the packages in such a way that there are no hidden inputs, so that people who build one package do not have the intent of a state, so that another person who comes in needs to first fully understand the state. So this is one part of it, and the other one is that we have to share it and make it the process count in the way of continuous integration. And we have started with the one package quite some time ago. This is our showcase package currently. It's just a small one who's calculating running time. So if you have the typical problem of you have two cities and you want to know how much time the train needs from one city to another, that we can run the physical time which the train will need, and also the forces involved and the energy involved to make the train run. So, but the main point here is that this package should take those design rules from the slide earlier and apply them. And so we have this architecture where we only have this one function. You give it a train, you give it a path where the train should run on, and then you get a time back. So this is one of the architecture rules. Then, of course, we built in some tutorials and put it into the Julia ecosystem. So this is where the Julia environment really helps to make it with the to integrate it with the continuous integration process. And of course, everything is open source and citable via Zenodo and so on. But we also made some deliberate choices on the formats the tool takes. So it's basically a JSON scheme. And this JSON scheme is a deliberate choice because most of the data in this domain currently still runs on Microsoft Excel. So this is the major pain point. And most of the people who are involved in in the stuff is computer science agnostic. So they don't really care what we are doing, but they do care about if they can read the data and manipulate the data. So that's why we choose YAML as a format for human readability, but JSON schemas for the computer part, so that the machine readability. So we provided two packages already. These are the paths and the rolling stock so that we can put them both together and do the runtime calculations. And also this package can be adopted in such a way if somebody else finds a better model for modeling the physics later on. And this is also our current roadmap, in that case, Railmap. So we are currently at the loop to redo our package, so make it train runs 2.0. And after we've done this and also have a further look at the schemas, we can then move on to make the environment count. And for to make the environment count, we try to focus on the use cases for that. So we're interviewing people from the engineering domain to give us their use cases. And then later on, we can build the whole simulation stack, which might people actually want to have. But we need your help. So please help shape it. So please come to us with your use case, with your calculations, your validation cases. Everything is welcome. It doesn't have to be code, but we need the use cases because from these use cases, we can build up. We know what actually counts out there. We can compare to the real time. So if you want to help, this is the entry point. So that's already all I have to say. Just in summary, we have quite still a closed environment of tools out there. We have a starting point for the environment. We need use cases, and we also build it on use cases. We need the workflows to grow it. So please bring yours. And thank you very much for listening to me.
Thank you, Martin. Are there any questions? I'll come up there. Yeah.
So can you comment on the speed or performance that you have and that maybe what you want to have? So are you thinking of simulating single train tracks and how long they run, or do you want to simulate maybe the whole German grid or the European grid and then, I don't know, do research on how to optimize, or could you go to Deutsche Bahn and say we can make your trains more functional or something like that?
It's a quite low-hanging fruit actually to get performance out of it because current tools are not really that performant. So they are still mainly built in the 90s where they use different approaches. So this is quite an easy thing to do. So it's definitely a target because if it's so easy, then we will do it. And we want to build and simulate a complete network, but we have to also break it down for the small verse because the most ideas are more locally observed than in the whole network. So for instance, if you want to rebuild a station, then you actually need to know what happens. Use case in Germany would be Stuttgart, for instance.
Anybody else? All right.
Yeah, thank you for the great talk. It's a really good case you want to do there, I think. I'm not in the civil engineering, so I can't help you, and only 3 other people here in civil engineering, so not much people who can really help you, except maybe provide
Still people
software.
online, right? So.
Yeah, okay, right, that's good. So, but are there other plans where you want to spread this idea? Are there other conferences you plan to go to? What are your plans there?
Of course, we are mainly here because of the Julia environment and it's part of Julia, so therefore that's why I'm here. And of course, we are also on other conferences. For instance, the tool or the package train runs was also presented at a Railway conference in that sense. So I'm audience aware if that was the question.
Great. Good thing. Thanks.
Any other questions? I was wondering, I'll ask one. So what do you think like who do you think the users would be for this? Other like civil engineers or like train operators or who might be the because also when you start thinking about users, you start thinking about how to bring the Julia to them. So just wonder.
Of course, we have to bring Julia to them because we need the engineers to actually compute it. So the target is the people in the railway domain. So there are the operators, there are the engineers, there are the complete industry. So there are more people than you might expect, but their tool at hand currently is more Excel than anything else. So the idea to make it easy for them to interact with that, and this is main target. So of course, Pluto might be a way to do it, but it is an obvious choice. So, but the thing is, most people don't even know how to run Pluto. So, so it's an educational issue as well.
Yeah, for sure. Or maybe there needs you need some front end kinds of things like front end back end kind of implementation.
But still, the engineers need to learn how to code. So
Yeah,
it's vice versa.
Sure, sure. Yeah.
We have to meet some in some
Yeah,
place.
yeah. No, it's really it's great. Yeah, thanks for sharing it with us.
Thank you very much.
All right. Anybody else? All right. Okay. Well, yeah, we'll wait a couple minutes and then kick in the next speaker.
So my name is Sören Schönbrot, and I'd like to make you excited about Julia GNSS. Julia GNSS stands for Global Navigation Satellite System. I've brought with me a software-defined radio. It looks like a USB stick. You can plug it into your computer. And I've attached an antenna to it. And I want to show you how to get from these raw samples to a position. I actually wanted to do a live demo, but unfortunately, the GPS satellites won't reach within this building. So nevertheless, I've recorded a file. It's around 2 gigabytes of data. This is what that signal looks like. So what you can see here is the spectrum. It's in the frequency domain. So and then this is the center is the GPS L1 frequency, and I recorded it with 10 megasamples per second. On the y-axis, you see the power spectral density, and what you see here is essentially nothing. It's just noise. What you see here, right? It's a flat line, and a flat line means there's no signal, no wanted signal in it. Well, that's a little bit untrue for this case because you need to know that the GPS satellites just send out with 60 watts, and that's like a kitchen bulb, you know. And so what arrives at your antenna is just in the range of femtowatts. So the signal that you receive in your antenna, that's well below the noise floor. It's roughly 20 dB below the noise floor. And how can you decode something that's well below the noise floor? Well, you need to know what it is saying, right? And that's exactly it. So each satellite sends out a well-known code. For GPS, it's a code of that contains 1023 ships. And what you do to get it out of the noise floor is that you create a local replica, and then you create a matched filter, and you match it with your incoming signal. So I have a quick demo here. You see I have a local replica, and I move it on the code. I move the code as and up until I found it matches with my incoming signal, and then this integrating this then moves it up above the noise floor. But that's not only it. I also need to search the Doppler space. So either the satellite might move towards you or away from you. So you also need to search the Doppler space. And here's an example of that. You can see I searched the Doppler space from minus 8 kilohertz to roughly plus 8 kilohertz, and the code phase space from 0 to 1023. And you can see I searched for all 32 satellites. And in this particular case, I found roughly 10 satellites. Some of them have a high signal to noise ratio, like this one here. And you can see it's all live run on my laptop here. And some others have a fairly low signal to noise ratio. The dot here is exactly where the signal has been found. If we zoom in a little bit on maybe on a signal with high signal to noise ratio, we can see that it is a triangle, and that comes from the correlation with incoming signal. So if you correlate two ship sequences with each other, you get a triangle. So you need to know the acquisition is really computationally expensive. You search the whole Doppler space, you have to search the whole code phase, and you find a single peak. So what you do is, after you found the signal in Doppler and code phase space, you usually track it. And that's what it looks like. You just have 3 correlators, the so-called early, prompt, and late correlator. And this is a lot less computation expensive than all the correlators that I had calculated previously. The early and late correlators are there to align the code phase, and the prompt correlator is used to align the Doppler and also to decode the signal, the navigation signal. So once you have the acquisition and you reliably track the signal, you can start decoding the navigation bits. The navigation bits only come in at a really low rate. It's only 50 bits per second, so it's a really slow connection. And it contains information about the clock offset of the satellite. It contains information about the orbital information where the satellite is going around the Earth. That's subframe 2 and 3. And yeah, once you've then decoded all the necessary information, you know exactly where the satellite is at a given point in time. So this is then the on the receiver side. So once you have a position fix, so you're on the you're on the left side, you see a continuous panel of all the carrier to noise density ratios for the satellites, and then you finally get a position down here. It's this is in Netherlands. I also have a map down here, and if just we can zoom a little bit out. This is Unicode maps, JL. If you ever want to have a map in your terminal, you can use it. So you can see here where the location is, the position fix is somewhere in the Netherlands, and somewhere at the city of Leiden. And what you get as well is, as soon as you have your own position fix, you can also say where the satellite is coming from. So, for example, satellite 7 here is coming close from the zenith. Yeah. So why I've chosen Julia, it's probably the same story for most of you here. I came for speed. You know, the processing 10 mega samples per second is really demanding, and doing this in real time is hard. But I stayed for multiple dispatch, and I want to give you a quick example here. So as I said, in traditional GPS to process traditional GPS signals, you only need 3 correlators, the early, prompt, and late correlator. But for the purpose of this demo here, I wanted to have a higher resolution of the triangle. And so this is the triangle that I have here. And you can see that it has a much higher resolution than just the 3 correlators. And it was only, you know, a few lines of code to add the struct triangle correlator here in this case, and add 4 more lines, and that's it. It's really cool. So to conclude, we started with a flat noise floor and a signal that's 50 times weaker than the noise hiding it. And in the end, we ended up with 10 satellites decoded, a position fix, and the time in nanoseconds. Julia GNSS is a GitHub group. It consists of multiple repositories to make this work, and most of them, all of them have reached version 1.0 or are past it. And what we are working next is I'm working on hardware correlators, so that the correlation is actually done on an FPGA. And a colleague of mine is working on vector tracking loops. Yeah, and I think the future vector tracking loops actually landed yesterday evening, so that's already in. So if you ever wanted to yeah, work with it, you are happy to do so.
All right, well, let's thank Soren. Are there any questions? Comment.
Hi, thank you for a great talk. How do you see the future of Julia and software-defined radios and GNS? Do you think there will be more people using it? Do you know of any applications, or is it like a lot about the research and improving the algorithms?
That's a good question. I can say for Julia GNSS, it's Julia was a great fit because it's really flexible with what you can do. Just the correlator example that I gave you. So I think it works pretty well for these kinds of things. One thing that's a little bit difficult to work with is the garbage collector, especially if you work with software-defined radios. So you need to pull the samples into your memory really fast, and the garbage collector, it stops the whole Julia world for a few milliseconds, and if you are not pulling the samples in fast enough, then you get overflows. And yeah, this is one part where Julia needs to get better, maybe. But other than that, I think it's really fun to work with signal processing because you have all the matrices and vector things that are far easier to work with than in any other, or most of the other languages.
All right, any other questions? Cal?
Maybe I missed it, but what's your background? Why are you doing this? Are you on a university doing research, or is it a fun project or a hobby project?
Yeah, so I started with a GNSS receiver during my when I worked at university. And then now I'm working for JuliaHub because JuliaHub had back then when I switched from university to JuliaHub, it had a similar project, and I kept this open source work alive and still working on it, and because it's just fun.
Okay, yeah.
Okay, any other questions or comments? All right, thanks again, Soren.
my talk. I'm delighted that you're all here. A lot of you I've already met at this amazing conference the past couple of days. For those who I haven't yet had the pleasure to meet, I'm Nat. I'm a systems engineer. I work for a company called Prismatic, and today I'm going to be talking to you about how we use Julia in the simulation and modeling of the solar-powered aircraft that we're developing. So I'll start with a few words on who Prismatic are and what it is that we do. So Prismatic is a UK-based business. We're located in Alton in Hampshire, but we also have a location in Oxford. Prismatic was acquired by BAE Systems in 2023, which is the UK's largest defense contractor. Now, we're developing a persistent high-altitude solar-powered aircraft, and I'll explain a bit more what that is. So it's called Phaser 35, which stands for Persistent High-Altitude Solar Aircraft, and 35 is the wingspan in meters. So it's quite a large aircraft, right? So it's got the wingspan approximately of an A320, but unlike an A320, it only weighs 150 kilograms. So it's super light. It's all carbon fiber, basically. It flies in the stratosphere between about 60,000 and 75,000 feet above mean sea level. It stays in the air with solar power only. So it's got solar arrays, it's covered in solar arrays. It uses those to power itself during the day and also collect sufficient energy to store in the batteries, which it then uses to stay aloft during the night. We can operate continuously for durations of up to 6 months, and we pretty much only need to land for maintenance. So there are certain latitude bands in which we can operate year-round, and obviously those latitude bands correspond to the amount of sun that you get. The primary applications of this aircraft are in the surveillance and communications areas, and it can also be used for things like wildfire detection and disaster relief. We can carry a payload of up to 15 kilograms, and our primary competitors, so to speak, are low Earth orbit satellites. So unlike low Earth orbit satellites, we stay on target all of the time, not just for a few moments every 1.5 hours as the satellite goes around the Earth. And we're also about an order of magnitude closer to the target. So we're significantly more cost effective because maintenance is a lot easier, it's a lot cheaper to launch it. And yeah, so basically that's what we're competing with. Now, what does any of this have to do with Julia? One of the things we do is we need to model the performance of this aircraft. So we need to answer questions like, during what days of the year can we operate at what latitudes, and how low do we have to go during the night? And for that purpose, we have developed a Python performance model a few years ago. And that performance model also includes a solar array model. So what the solar array model does is it just predicts how much energy you get from the solar arrays at any given point in time and at any aircraft orientation. That's not the only solar array model we have. And to explain this further, I need to give some more background on how this aircraft is operated. So we have a ground control station, which is basically just an ISO container. And you can see that's in the image here. So this is an image of the test site in New Mexico in the US, where we do all our flight testing. And one of those containers in the far left is our ground control station. So for test flights, we need to train the flight crew, right? Because even though the aircraft can operate autonomously, the flight crew is needed to monitor the aircraft systems, respond to any warnings, cautions, and alerts, and any potential system failures. And for that purpose, we have developed a flight simulator. And that flight simulator is developed in Simulink, and that also includes a solar array model. Right, so we have two solar array models, one in Python, one in Simulink. So we said, right, this doesn't make sense. We got to fix this. And you might have already guessed it. We decided to develop a third solar array model. So then the question arose, um, what sort of language, what technology do we use for that? And one of the requirements was that it needs to support real-time simulation for the flight crew training simulator. And so that ruled out Python because we don't have a lot of performance margins and it needs to be fast. Another requirement was that it needs to be amenable to version control. So we wanted something that is text-based, and that ruled out Simulink. Then we also wanted something like many of you that is accessible to non-software developers. So that pretty much ruled out C++ or Rust. And then, and this is more of a nice to have, but we also wanted a healthy open source ecosystem and modern language features. So that pretty much ruled out MATLAB. So why not Julia? And one of the big selling points for Julia for us was Julia C as well, because that would allow us to get sensibly sized distributables. Like anybody who's packaged a Python application knows that you end up with something that's several hundreds of megabytes large, and it's just not nice to work with. So I'll briefly explain how the solar array model works. We basically define the aircraft geometry in a software called OpenVSP. For those who are not familiar with it, it's basically a parametric conceptual aircraft design modeling software. And alongside, we also have a configuration file that defines all of the solar array relevant parameters, like roughly where they're located, what the voltage current curves are of the individual cells under lab measurement conditions, what those measurement conditions are, and things like that. Then we take those two pieces of data, the geometry and the solar array specification, and we process them with a Python script. And we use OpenVSP's Python API to basically calculate exactly where each cell is located in 3D space and how it's oriented and what its characteristics are. And then finally, we have the piece of Julia code that processes all of that information and then calculates a voltage current curve for the entire aircraft. And that also includes ray tracing, because one of the things we need to work out is at any given aircraft orientation, there will be arrays that might be shaded by other pieces of the aircraft. So, for example, at low sun angles, so early in the morning and late in the evening, which are particularly critical for us, we might have, for example, one wingtip that is shading the other wing, or another component of the aircraft that happens to contain solar cells on it. Now, another question to answer is, how do we integrate that with our simulator? In fact, that was the very first question we needed to answer, because if we don't get that right, then Julia is not an option. So we decided to go with the FMI specification, so to integrate it as an FMU. For those who are not familiar with it, FMUs are basically a simulation interchange standard, so I can have tool A, which has a simulation model in it, and I export an FMU, and then I can import that into tool B, which then simulates that FMU. So my first plan was to use a package called fmi.jl, which allows packaging Julia code as FMUs. Unfortunately, that didn't work so well at the start of this year because there was something about the package relied on Julia internals, which had since changed and didn't compile. So I fixed that, and then there was another issue. I couldn't get it to run. So I said, right, I need to actually understand the FMI specification. So I went through the spec, and Modelica provides some reference FMUs on GitHub, which are written in C. So I started with one of those, and then used Julia C to compile a basic Julia function export it as a library, and then link that against the C code. And that worked quite well. Some further general comments on the experience with Julia C. So all the stuff in base is typically fine, but if you want to bring in third-party dependencies, like for example for the ray tracing or geometry stuff, then they tend not to be compatible with Julia C. So you have to, either fix the packages or develop your own solutions. But I mean, we saw earlier this week that that's being worked on, and yeah, I think there'll be a lot of good developments in that space. So, for example, one of the things was the JSON package wasn't compatible with Julia C out of the box. So I had to basically write my own that would fully statically resolve all the types at compile time. Okay, that's it. If you want to learn more about Prismatic, there's a QR code on the left. If you'd like to connect on LinkedIn, there's a QR code on the right. Thank you very much for listening, and I'm happy to take your questions.
Thanks, Nat. Thank you very much, Nat. That's cool. We have any questions? Yeah.
Hi, thank you for the great talk. One question is how the aircraft efficiency varies with altitude, because I think you said at some point how low you need to go during the night.
Yes, yes. So the reason you need to descend during the night is because you want to minimize your power consumption, right? So you know how long your night is, right? You know how much energy you have in your batteries, and so you need to make that last for as long as possible. So you need to minimize your power consumption, right? So the lower you fly, the denser the air, and so at the same lift coefficient, the lower the airspeed, right? And power is directly proportional to airspeed, so that way you minimize your power, right? Now, you might ask, well, why don't we just, fly at sea level, right? The reason is twofold, really. Firstly, we always need to stay above the weather, right? And because this aircraft fundamentally is very fragile, it's super lightweight, and we don't want any turbulence, right? And the second reason is more pragmatic. We always want to stay above controlled air traffic, right? So yeah, that limits our minimum altitude.
Yeah.
Thanks for the nice talk. I had a couple of questions about your Julia C experience.
Sure.
First of all, did you manage to get rid of all compilations at the start of invoking your Julia C process? Because we didn't. And the second thing was, did you manage to use trim successfully? Because we also didn't with our application.
Okay, so yes, I managed to use trim successfully. In fact, that was one of the requirements, because when I first started out with fmi.jl, even though I wasn't able to get the FMU to run, I got an order of magnitude of how large it was going to be. So that was a 1.6 gigabyte FMU, right? So every time I run my simulation, I press play. I don't want to wait a couple of seconds for all that data to be unzipped before I can actually start the simulation. So getting trim to work was one of the requirements. And I think what worked well for me was just starting off with a minimal example, right? A minimal Julia function, then gradually expanding it. Because even if you just bring in maybe one function from one library that is not Julia C compatible, suddenly you have like 400 verifier errors, right? So that the developer experience could be improved there. But I think the key is to start off small, get something that works, and then gradually expand it.
Thanks, that's very interesting. I think that was exactly our problem. We started with quite a mature application, and then we were trying to throw things out to get trim to work. We didn't quite manage to get there.
All right. Well, I think we'll wrap it up there. Thanks, Nat, again. Philip's going to talk about solid mechanics.
Yeah, thanks for coming to the talk. So this is joint work from our support team, basically, with the team of data-driven mechanics at the Institute of Applied Mechanics at the TU Braunschweig. And it's all about data assimilation and constitutive model discovery. And so, as a short introduction, this is our problem setting. We have a mesh, not super finely resolved in this case, but all these yellow dots, that's just the sensors we might have. So we do a measurement, add a few displacement sensors. Those may be noisy, so they have some inaccuracy. And so we have very sparse data. So a bit similar to Jasper's problem. We know the mean traction because we did the experiment. And we, in principle, know the PDE because it's solid mechanics, but we might not know the strain energy density function of the material model. And of course, we also know from the mesh and the sensor locations how to map from one to the other. And then our goal is identify the parameters of our strain energy density function and match the projection of our FEM solution to the measurements we have. And so conceptually, this is kind of running in a loop. We do an initial guess of our material model. Then we forecast. We have a polynomial chaos expansion surrogate, just so we don't have to do Monte Carlo with like 10,000 iterations or something. That would be quite costly. So the PCE takes around 50 samples, a lot better. And there we apply a stochastic traction. So we say traction is normally distributed around what we started with, and we assume like the measurement isn't perfectly accurate, so it might change a little. And then for this one, we check, does it match our data? If it does, we're done, which usually shouldn't be the case with our initial guess. Otherwise, well, very good guess, I guess. So if that's not the case, then we'll assimilate our state. So we'll correct this solution we have because we're missing a full field solution from our data. So we'll try to kind of match our solution on the full mesh closer to our data. And then we have this solution to plug into the residual to then solve an optimization problem to do model parameter identification. And for this, we use what's called Euclid. So it uses a very large material model and then tries to come up with which parameters actually are of interest. And so we wrote this Julia packet for it, and it uses UM-Bridge as an interface. If you're not familiar with it, that's the uncertainty modeling bridge, which basically aims to separate all your UQ code from your forward model, because you might want to change that to something completely different. And for us, that's like the use case, thinking somebody might come, have done an experiment, and say, hey, we already like implemented this experiment in solver XYZ. So we wouldn't want to re-implement if they already have that. And then what would the FEM solver need to provide for us, or hopefully need to provide? Obviously the forward model. So given a traction, give me back the displacements. A residual model. So given the traction, given our solution, and given the guess for our material parameters, how far off are we? And then optionally, to kind of use better gradient-based optimizers, a gradient with respect to our material model would be great, but we can also use gradient-free methods. They take a lot longer, but they work. And then also what would be great would be a projection model, so we can make sure that whatever like finite element definition they used matches to our projection. If not, we'll use a bit of FEM code and Gmesh to load in the mesh and compute that on our side, assuming the element definition is close enough, which for like P1 elements it should be. And it provides all the functionality we need. So the sampling with our prior or our forward model, the polynomial chaos expansion, and both the subsets of StatFem for the assimilation and Euclid for the discovery. And all the code for the examples I show is available as examples in the repository. So if you want to check it out later, it's there. Okay, and so a bit more of an idea on this interface. We have a submodule FEM client just to make usage a bit easier, because the UMBridge, you have to pass vectors of parameters and everything, and just a nicer interface basically. And so we see we pass our traction and optionally our material parameters, and then that gets sent to a black box FEM solver. And you see a few logos of a few open source solvers you could use. You could also use closed source. You only need to write a little bit of UMBridge server code to like receive the data and start your simulation. And then for the FEM model, that solves the problem and returns our displacement. And for the residual, we give it our displacements, our material parameters, and maybe the traction. Maybe the traction is built in as like the, just take the mean traction and be done with it. Evaluate the gradient and return back the gradient. And that model also can then, or evaluate the residual. And UMBridge allows you to say, well, I don't only have the evaluation, but I can also provide you with a gradient. And then we can check on our side, is a gradient provided? If the model doesn't, and you try to do gradient-based optimization, we'll say, wait, don't do this. Use a gradient-free solver instead. Yeah. And so for the data assimilation part, what's our goal is a full field displacement. So a full solution vector for each of the nodal degrees of freedom. And what we do is we have a polynomial chaos expansion, and this kind of is our surrogate model to then have the statistics we need to go into that to perform this Gauss-Markov-Kalman filter. And that combines our sparse and noisy measurements, our sensor data, so what's the noise distribution, sensing inaccuracy, where are the sensors, so the projection matrix, and the surrogate. And then here you can see some results. So in yellow, we have the forecasted PCE and its confidence interval. And that was done with a linear elasticity model. So a bit far off from the Mooney-Rivlin model we used for the synthetic measurements, which are the black dots. And then we only had 14 sensors, so the ones I showed a few slides before. And we only have 3 sensors like on the bottom piece of our domain. And we can see in blue, that's the posterior, so this Bayesian inferred assimilated state. And the noise is quite heavy. So you see the displacements down there are 5 and the noise is 0.5. So it's not surprising that the points aren't on the line, because the points have a lot of measurement noise applied. But you see that it's matching greatly. We could have used less measurement noise, but then you wouldn't see a confidence interval for the posterior. So we kind of exacerbated this for this sample, so you can actually see something. Okay, now to the model discovery. One thing you could do if you kind of know the model, because you know your material in principle, so you think, okay, this should follow material law XYZ, is to only do an optimization on the residual. But if you have a composite material or something and you don't really know, what you can do is to use a model library, so a strain energy density function with a lot of parameters. So pick and choose from different material models, add those all up with multiple parameters, 10, 20, doesn't really matter. And then you kind of do this lasso regularization. So you penalize in your optimization goal that you have a lot of parameters, basically. And then you solve an optimization step for each of these lambdas, which just is a kind of scaling between the actual residual and the lasso penalization. And then what you also do, because you want to get only the parameters that matter, you set a threshold, for which we use 10 to the minus 9. And if a single parameter is below that, you just say, okay, this is clearly not important to the model. I'll just zero it out. And then you can calculate a model selection criterion. We currently have two, so the Bayesian information criterion and Ikaika's information criterion, but you could have multiple others. And then based on what you got from this model selection criterion, you choose the material parameters that had the kind of lowest one out of this lasso pass you followed. And so to show that this works, we now used noiseless full field measurements. So we solved the same Mooney-Rivlin model, but we didn't then sample it at some sensor locations. So the true values you can see are 0.3, 0.2, and all the others are basically too much, and then 1.5. And then the model library was a 10 parameter Mooney-Rivlin. So that's like all the others you see that are 0. And we used for the optimizer an interior point method with inner BFGS. So all that comes from opt-in, so fmin box of BFGS. And well, if you look at the parameters, I'd say we were quite successful, because if you look at the errors, they're all in a reasonable range. And now we want to put those two methods together. So we have one to get more data from a few measurements, and one to then, if we have full data, get a new material model. And because this now is a harder problem, we use a few more sensors, 38, and less noise, because we don't want to kind of exacerbate this. And we only needed to sample 50 PCE samples, and otherwise the settings are basically all the same from the other examples. And these are the results. So you see a nice parameter convergence of the three important parameters. And you also see that the root mean squared error converges nicely. It could go to something lower, but well, these are the first results, and I think they're quite good. And so to conclude, the PCE is a really good surrogate model if you don't want to do tens of thousands Monte Carlo samples. The StatFem posterior gives a usable approximation of U to then do the parameter identification, and Euclid is also able to get rid of most of the parameters that weren't there in the synthetic data. So overall, for the synthetic data, we can see that we can rediscover the original material model, even though we only had very few measurement data points. And with that, any questions?
Thank you, Philip. Take a question or two here. Hey, sorry, guys.
Hi, yeah, two quick questions. First question, how many parameters are you estimating? And second question, how long does one forward pass simulation take, approximately?
So we have this material model with 3 parameters. So a simple Mooney-Rivlin problem, and then we used 10 parameters, as you can see in the Euclid, for the bigger one, just to see if we can get to the ones we want. As for the runtime, I ran this in a hotel room and I didn't time it. I just got it to work this week, so we'll have to check. But the Euclid itself, if you have a reasonable solver, it also takes a reasonable time of 60 seconds or something. So still quite okay. And that, of course, evaluates a lot. And depending on what your forward model might be, that might take longer or shorter times. Okay.
All right, thank you very much.
Since you're the last to speak, I'd say thank you for this nice session.
All right, great. Thanks. All right, well, first, it's been a pleasure hosting this Engineering with Julia mini symposium. Thanks to all the speakers, much appreciated. Also, thanks to Andres and Julio for AV, although it sounds like I'm getting some feedback right now, right? So you did great the whole time except for right now. Anyway, yeah, I'm going to just talk about a implementation in Ferrite, a special element that we're using. Um, I'm the I'm, I'm the CEO of Run to Solve, and we're often asked to. So I'm a civil structural engineer, and we're often asked to evaluate or consider structural systems like this. So there's lots of like beams, columns, connections in a building, and we're asked to consider how that building will perform in an extreme wind event or an earthquake or heavy snow. And so we're usually using commercial tools to predict performance, but we're becoming more and more interested in doing it ourselves. And so I gravitated to the Julia language a while ago, mainly I was interested in solving ODEs and then I found Ferrite here, and Ferrite.jl was like a really welcoming finite element package framework. Why did we want to use it? It has some really nice features like automatic shape function, interpolation stuff, Gaussian quadrature, like numerical integration. It's very convenient degree of freedom handling. And also is a very like active and welcoming community, I would say. So those are all very appealing. And if we're trying to model a big building, we need like a reliable, accurate building block. So, you know, we're always trying, in our world, we're always trying to discretize and solve these systems of equations. So, yeah, so we started with something very simple, just a triangular element here. It looks simple, but it's ends up being maybe not so simple, especially since the kinds of buildings and structural systems we work on are also thin-walled, so meaning that they have buckling that you need to consider. So you need to include a little bit more information in like compared to like a typical like finite element. You need to, so here's like an example where like you may just want to use linear shape functions to interpolate between deformations between nodes, like N1, N2, N3, but for the kinds of things that we're working on, and also if we're trying to match our commercial programs, so we often use like Abacus, for example, and there's an S3R element there. And so we're trying to at least align with that. That's almost like our ground truth. And so, yeah, we know we need a little bit more information. So then we can want to add more information with N4, N5, and N6. Yeah, and so what's cool is like that was like very easy to do with Ferrite. So like found this piece of code as an example and then just modified it a little bit. And so we could take all of those interpolation functions and just plug them in. And then because of all of the features or automatic features in ferrite, you can just get things like automatically get the derivatives of the shape functions. So this is very exciting, right? Like, so you don't have to do too much work. You just plug in your special element, and you can get the information you need to calculate deformations, which come from strains and or yeah, deformations, strains, and then stresses. So yeah, like it's very cool. For then, so one other thing we need. Well, um, uh, we also, when we're trying to consider geometric nonlinearity in these types of predictions, so that geometric nonlinearity results in the buckling stuff that I was talking about previously. You also need like so usually we're working in like the mechanicsy world like an elastic stiffness matrix, but you also need to a geometric stiffness matrix that like can degrade stiffness, or if you're pushing on a column or if you're pulling on a member, then you get actually like it adds to the elastic stiffness matrix. But anyway, this is just an example of one of the terms that are included in the package that we wrote, this tri-shell finite element. This considers like you can probably see if you're at all in tune with mechanics, you can see some familiar things like that the stresses are influencing the stiffness. So you can see some stresses here, sigma x, sigma y. And you can also see that we're multiplying some strainish terms. So that's like the nonlinear part of, or the higher order part of the energy balance that's needed, that's used to derive this uh, uh, stiffness matrix. And then you can also see there's like a get determinant JDV, which is like the numerical integration part. Yeah, and then we're looping over this, all the different quadrature points in the element. And then we end up with two matrices, like a KE and a KG. And then from there we can do a lot of things. And I'll just show you. So here's like another picture of another kind of building that we're often asked to predict the behavior of. And you can see this is all like thin-walled steel, and like the limit states, the way that it fails is from buckling. So we need to be able to predict that. And yeah, so I'll just show you that. So the solution is we have ferrite. It's very like general. Then we wrote like a very specific element type, a flat-ish shell element with some geometric nonlinearity. We can get these parameters, the geometric or elastic stiffness matrix, and then if we wanted to just solve for like the elastic buckling loads, we can just simply do like an eigenvalue solution and get the modes and mode values and do something like this. So, and this is a big win for us. There's definitely more to do. But yeah, and you can see here, like, actually I can do a little animation too. I have to set down the mic, but first I'll just show you, like, this is what happens when you load one of these thin-walled members. If you've never, if like you've never seen that happen before, like you get these little bubbles along the length, and that's what degrades the properties. Here, I'll just, I don't know, might as well here. How much time do I have? I'm moderating myself. Okay, I got time. So you can kind of see that, right? So we, in this case, we're just compressing it, and all you can get all the, you can get, this is what we will call local buckling. There's many modes that we, or not many, but a few modes that we usually have to consider. There's also a mode where this is a C, and sometimes the C wants to open and close. That's a different mode, or it wants to like twist in like more of like a longer half wave. But We can predict all of this now with this element type, and we've validated it against the Abacus S3R for plates and for these kinds of C-sections. So um, yeah, so anyway. Yeah, so like this is this is pretty exciting for us. We have now some buckling capabilities outside of the commercial programs that we're using, um, and so where should we go next? Like we also need beyond this triangular element. It would be nice for the meshing purposes to have a quadrilateral element. Um, so there's also like the ability to easily connect like nonlinear solvers to ferrite because of this, like all the Julia packages that are really nice and powerful. So like we could impose initial geometric imperfections and run like a more like a Newton solver to like watch a progression to failure. And then if you're interested in that kind of progression to failure, then of course you may want plasticity to really predict the failure. And yeah, there's things like contact that are we rely on a lot. Like you could see in the building systems that we're studying, there's all kinds of pieces connected together. And for sure, we're also interested in, we are often asked these days to consider whole buildings. And there was even a presentation earlier with CFD, like you can imagine connecting CFD to a structural model of a whole building, and we could have a lot of fun. There's a lot of people working on high performance computing here. And so like all of this is very exciting. And that's what we're pondering right now. So that's it. And thanks a lot for attending my talk and for attending all the talks. And yeah, I'm happy to take a few questions if there are any. Thank you. Or we can just go to lunch. Christopher, see, this is what I'm talking about. This is the support I get from the ferrite community right here. Coming up.
So what advantages do you have with this over just throwing it into Abacus and just going from there? Like what do you gain from doing this? Is it just for fun or is it for?
I mean, we can save about $50,000 a year. So that's one reason. I would say. Yeah, I mean, that's a big motivation for me as the CEO of the company. But besides that, like we can also get to play around. Like, so in Abacus, the elements are relatively black boxed. It's hard to know what's going on. So, like you can see, if we wanted to play around with the interpolation functions, or even there's sensitivities in the elements with like reduced integration, like that kind of stuff. So we can play around with all of that very easily, and that's very exciting for us as like a researchy part, or even coming up with something better. Because Abacus is not perfect, obviously. So, or any of these programs. So, yeah, thanks. Great question. Anybody else? Yeah, I'm coming up.
Thank you. So if I remember correctly, in the introduction, you were mentioning like wind loads and these kind of things, earthquakes and stuff like that, which is something that we're also working on. And I was wondering what you use to like model these kind of things around the actual model of the structure.
I mean, for wind loads, it's relatively, we're often using just very simple, uh, even like equations and models that have like taken out all the dynamics. It's pretty much equivalent static loads on buildings. That's like the common way to do it. There's not much fancier stuff than that. And the earthquake community will run time history like of a whole building every once in a while, like considering the ground motions. Um, but a lot of it is uh, a lot of the dynamics of these events are converted to equivalent static loads. But with as with the movement towards like we're having more computation. We have more computational power, more tools. Like I'm seeing that there is a movement away or like more towards performance-based engineering where you could really like just take your building and run, yeah, really run all the loads more, yeah, like with more physics. All right, thanks everyone, and have a great rest of your JuliaCon. Take care.
All right. Good afternoon, everyone. My name is Ray. Today, I have the pleasure to chair this last afternoon session of the last day of JuliaCon. First, a few housekeeping notes. I will be showing you the time cards, which are the time actually left for your session. So if you're doing a long talk, I will show you 15 minutes left. So that means you're halfway through. And I will show you 5 minutes left. That's 5 minutes to the end of your slot, including question and answering. So that's important. If you're giving a short talk, that means it's probably now you should really wrap up. If you're giving a long talk and you see the 5 minute sign, that means you should probably start taking questions. But then I will remind you with another sign. Another note is while I start the question answering, I start the question answering session. The next speaker, could you please come down to get your headset set up and get ready for the next talk. Without further ado, let's introduce the first speaker of this afternoon session, Dr. Benedict Christopher Paul, and telling us about Target, a Julia-powered pipeline built with a hybrid machine learning method for M. tuberculosis drug resistance prediction. Dr. Paul, the floor is yours.
Thank you. Good afternoon. I'm Paul, Assistant Professor, Department of Biotechnology, Faculty of Biomedical Sciences and Technology, Sri Ramachandran Institute of Higher Education Research, Chennai, India. I have done this work in collaboration with Dr. Sivakumar Shanmugam, Scientist, Department of Bacteriology, National Institute for Research in Tuberculosis, Chennai, India. We have developed an application called JuTarget, a Julia-powered pipeline with a hybrid machine learning method for Mycobacterium tuberculosis drug resistance prediction. We have also filed an Indian patent for this novel machine learning method. Drug-resistant tuberculosis is a clinical challenge and a growing health concern, and it has been one of the most significant challenges in modern medicine, threatening global health security and reversing decades of progress in TB control. Around 500,000 cases, drug-resistant tuberculosis cases, are reported globally, which requires complex and urgent workflows. When first-line drugs fail, the clinicians are forced to rely on the second-line drugs, which are expensive and with severe side effects. So we are in need of rapid diagnostics. Without rapid testing, patients receive standard treatments that are completely ineffective against resistant strains. Delaying targeted therapy leads to extended patient suffering and high mortality, ongoing community transmission of drug-resistant tuberculosis, further amplification of multi-drug resistance. The complex pipelines for this critical problem is a challenge. We collect sputum samples from TB patients, and traditionally, we use lab culture methods which have a very slow turnaround time from 3 weeks to 3 months, delaying critical treatment. We do have modern techniques like whole genome sequencing and targeted NGS, which are highly fragmented, complex, and hard to clinically validate. Among these two techniques, targeted NGS is preferred because targeted NGS focuses exclusively on known resistant loci, greatly reducing the sequencing time. It also avoids excessive genomic data, and it dramatically lowers the cost, making it a highly practical tool for routine diagnostics. While targeted NGS yields raw FASTQ data quickly, now the delay is shifted to complex bioinformatics analysis, setting the stage for JuTarget. We do have various bioinformatics tools already in use, which are mostly Linux terminal based applications. And the people who use those applications are microbiologists and they are not the tech savvy people. So we considered those limitations and we have included a graphical user interface, a Julia native analysis to have high performance computing, and a machine learning model to predict drug resistance. Ultimately, the reports are to be read by the clinicians. So we generate the report in a PDF format with a list of drugs. In our pipeline, we have integrated standard bioinformatics tools, which are mostly either written in C or in Python. We have included a Julia native module for filtering and further analysis, and our machine learning model before the report is generated. The whole pipeline is containerized in Docker. The drug resistant tuberculosis is due to various mutations in the bacterium, Mycobacterium tuberculosis, and those mutated bacteria are called variants, and those variants are already listed in the WHO, World Health Organization catalog, where they have a list of drugs, which drug is resistant to which variant. So in our application, we have a two-tier classification system in that in the first tier, we just do a lookup in the catalog. And if there is a match for this variant, a report is generated, which prioritizes the known biological evidence and directly identifies high confidence mutations. But in reality, these mutations are very frequent and we come up with new mutations in the microorganism. So those newly mutated microorganisms are called novel variants, and most likely those novel variants may not be there in the WHO catalog. So in that case, our application will turn to the tier 2, where we have integrated a predictive model which gets engaged only for novel variants. This predictive model we have trained with a set of 30 biophysical properties of the amino acid change, and we have applied random forest model to classify the mutation's impact. And this hybrid method is the subject of our Indian patent. We trained and tested the model, and the model was optimized to maximize the recall to ensure that potentially resistant cases are not missed out. And we found that there is high recall for fluoroquinolones and rifampicin, which are regularly routinely used tuberculosis drugs, which shows that there is robust predictive power for novel variants. We also carried out an implementation validation where we did a head-to-head comparison with the established pipeline in our collaborators laboratory, which is a Perl-based pipeline. And this validation was carried out with a set of 224 clinical isolates and 56,390 variants. We found that there is 100% concordance, which shows there is accuracy and reproducibility of our Julia implementation. Traditionally, these tools have been written in either in Python or in C. Some are in bash scripts, which are slow and sequential execution, which are difficult to validate and distribute. We have implemented our Julia ecosystem, so it gives a high performance out of the box, which is easy to validate and deliver. The graphical user interface eliminates the need for our command line expertise, making the pipeline accessible to clinical and lab-based personnel. We have integrated a true parallel processing, replacing the slow and sequential execution of traditional scripts. And we have also integrated a dynamic resource management, wherein we have allocated 4 GB per sample, and it dynamically scales a number of samples up to 8 based on the host machine's RAM availability. Because the application is Dockerized, it ensures 100% reproducibility in the scientific results. there is a small demo video which shows the application in action. As I said, because the application is Dockerized, can be installed on any machine at ease. And as we install the application, the input-output folders are created in the home directory of the user. And once it starts in the local host, the application can be opened using any browser. And once the graphical user interface loads, the user can just click the Start Analysis button and the pipeline starts. As I had mentioned earlier, the application will run the number of samples depending upon the RAM availability. If the RAM is very less, it will run at least one sample and put the other samples in queue. The user will also be able to see the status of the analysis as it runs. And we also generate a log file for every sample. Once the pipeline completes all the samples, the user can view the results using the View Results tab, where you have a table with a list of drugs and its result, resistant or susceptible, and also the mechanism of resistance, whether it is from the WHO catalog or it is A predicted. This result can also be taken as a PDF file, and that PDF file can be sent to the clinicians for easy reporting. Hence, our application, JuTarget, is a scientifically validated tool with a novel machine learning method and a Julia native scientific core. And this work demonstrates Julia's power for building complete, reproducible, and scientifically validated biomedical applications. In the near future, we'll deploy this JuTarget in a clinical research setting and expand the machine learning model. Thank you.
Any questions? We have time for a few questions. I have one. So you mentioned that the main motivation to develop this toolkit is because of most of the available tools are in Python and C.
Yes.
And is there anything that can be kind of ported or reused or like connected into the JuTarget, or is it supposed to be replacing them? Because the performance is
No,
much better.
currently, we are not aiming to replace those tools because we have just integrated them. Because if we are going to come up with a new package in Julia, then it should be published. Otherwise, we will not be able to satisfy our collaborators. So we can, in the future, we can come up with new packages and publish them, then integrate. So currently, we are using Julia as a manager that will run the whole pipeline. And the last step, we have integrated Julia Core, where just for filtering and analysis.
Yeah, thank you.
We will replace it in the future.
Thanks for that talk. How easy do you think it would be to alter the pipelines if I want to call SMV and CMV or change the algorithm for variant calling?
For variant calling, currently we are not going to replace, as I said. If at all we have to replace, then we have to come from scratch. Like for every organism, there is a reference human genome, tuberculosis genome. Then we have to, for every organism, we have to come up with a VCF file. So currently, we won't be able to do that. So.
Thank you. Let's thank the speaker again.
Thank you.
All right. Our next short talk will be given by Nathan Zimmerberg on what's new with Median.jl, a coarse-grained cytoskeleton simulator. Please, the floor is yours.
Hello, I'm Nathan. So I'm going to be talking about Median.jl and the kind of coarse-grained cytoskeleton simulations that we do. So here's an example of the kind of simulations that Median can run. So in the center, there's a actin filament. That's the kind of blue double helix structure. And that's inside a membrane vesicle in this simulation that's represented by the red triangulated mesh. And then there's also these white particles that are going to diffuse around on the mesh. Okay, so as the simulation runs, the actin filament is growing, and when it hits the edge of the vesicle, it buckles, and it ends up coiling into this kind of ring structure. And something else interesting that happens is that the actin filaments pushing against the triangulated mesh creates a barrier for these white particles to diffuse. So it kind of divides the membrane into these two separate compartments. Okay, so the main kind of computation we're doing in these simulations is solving Newton's equation of motion. So F equals ma. And we also add in a friction term and some random noise. And the algorithm is very simple. It's leapfrog-like called BOAB. So our time step is roughly 1 microsecond for typical systems. And there's 3 types of steps. One is we take all the velocities of the different particles and we kick them by the force. The other step is this A step where the particles just drift along their velocity vector. And then there's an O step where the velocities get scaled to count for friction and there's random noise that's added. Okay, so kind of on top of this, there's also a grid of voxels where we do stochastic reaction diffusion dynamics. So this is a cross-section of a T-cell mesh with the nucleus in the center. And each one of these boxes is a 500 nanometer voxel that we keep track of the counts of various diffusing species. Okay, so I'm going to be talking about one of the packages that we created for Median called simplex cell lists. So the problem that this is trying to solve is in our simulations, we can represent the different objects with these 3 primitives. So we have points that represent particles when they're inflated, so they become kind of spheres. For the filaments, they're made up of a chain of cylinders. So we represent those as inflated line segments. And then the membrane mesh itself is made of triangles. And we want to have a force function that prevents these from kind of passing through each other. So those are called the collide forces. Okay, so there's 3 types of objects. So you'd think we'd need kind of 4 or 6 different force interaction terms. But it turns out that thankfully the line triangle interactions and triangle triangle interactions, since triangles are just made out of points and lines on their boundaries, you can kind of decompose those. So simplex cell list has some very nice fast differentiable functions for the energy of kind of points, lines, and triangles interacting with each other. It roughly looks like the following kind of spring-like equation where there's a spring constant, and then we look at the minimum distance between these different objects. There's an interesting kind of extra smoothing term that's added for the line-to-line case, because the minimum distance between 2 line segments is not actually always differentiable in terms of the endpoints of the line segments. Okay. So the next challenge is, right, we have these force terms. How do you figure out which pairs of objects are kind of within some cutoff distance to be able to interact? So for that, I'm using this sort and sweep algorithm. So the main idea is that you have these objects and they each, you pick some axis called the sweep axis. And each one of these objects is going to have a start and end bound on this axis. So for example, object 1, it ends before object 2 is starting. So because of that, you know that there's no way for these two objects to interact. So basically, we take all the objects in the simulation, we calculate their bounds along the sweep axis, and then we pack those into uint64 values and sort. And in Julia, sort on vector uint64 is just insanely fast. So this works quite well. So after sorting it, you just kind of sweep through and maintain a list of which objects are kind of active at any given point in time. Okay. So this creates kind of like a filtering pipeline. So at the top, you have every possible pair of objects in the simulation. You can then filter out anything that doesn't have intersecting bounds along the sweep axis. Then you can look at the other two orthogonal axes and filter out anything that doesn't have intersecting bounding boxes along those axes. Sometimes you actually want two objects to overlap. So even though, so like the key example of this is in a triangulated mesh, the two neighboring triangles, you want to allow them to overlap without trying to push them apart. So there's a whole mask and exclusion system. And then finally, you do the actual distance check with floating point math. And if it passes that, then it gets added to the neighbor list to calculate the forces. Okay, so why are we using sort and sweep? So some of the bad things about sort and sweep is that the kind of scaling isn't so good. So in big O, it's roughly n to the 5/3. So the fully naive method is O of n squared. Ideally, you should kind of aim for O of n using some fancy like grid-based methods. But even though this kind of scaling isn't so good, it ends up being a lot faster than the naive method. And very importantly, it uses a very small and kind of predictable amount of memory. So the amount of memory that this uses just scales with the number of objects, even if your objects are a huge kind of diversity of size. So you can have very small objects and very huge objects in the same simulation. And that doesn't really hurt the memory usage. Okay. So that was kind of the simplex cell list package. So the next thing in Median is the link system. So this is kind of how we get the mechanics and the chemistry coupling together. So in Median, there's a concept of a place. So this is anything that has a kind of well-defined 3D position. So we have monomers on filaments, the filament tips, membrane vertices, anchor points, ball centers, and in triangle points. And then a link is you define a link type that has interactions between any number of these different places. And it can kind of, those interactions have three kind of aspects. So there's bonds, those represent mechanical interactions. So you can specify custom forces that get compiled down to fast multi-threaded kernels. There's collective variables. So these collect statistics about how the different places are wiggling around during the Langevin dynamics. And then there's reactions, where you give custom callbacks to kind of determine the rate that a reaction will fire. And then when a reaction fires, your callback will run and you can modify the system kind of however you want. Okay, so this is what this kind of looks like in Julia. So you define the place and give it these aspects of interactions and tell what type of places you want to be interacting. This is what the kind of reaction looks like. And so at the top, there's the effect. So that's the callback that runs when the reaction fires. So it takes this object C, and that's the context that kind of stores the entire state of the whole big simulation. And then you can use that to modify the simulation when a reaction fires. So here, where the actual link that the reaction fires at, this first function is updating that link. So it's changing the quantity of this num arp23 state in the link. You can also interact with that big grid of chemical voxels. So here we're updating the count of some diffusing species nearby. And then to figure out when these reactions fire, each reaction has a propensity. So that's kind of the reaction rate. And it's a product of all these different terms. So you can have a custom function to calculate the rate. You can just have a base rate. The rate can be a function of the volume. It can be a function of the number of diffusing species in the chemical voxel. And then you can also search for local objects in the vicinity of a reaction. So here, this phyla cutoff actin 50 means that this reaction requires an actin filament within 50 nanometers. Okay, so all these terms get multiplied together. And because it's just a big product of these different terms, Median can do some cool factorizing tricks to build a super efficient sampler for these different reactions. Okay, oh, and for the kind of nearby object detection, this is also using simplex lists. Okay, so this is a simple example. I don't know if I have time to go over, but I'd like to thank my advisors and the current and previous group members who have helped with Median. And, yeah, any questions?
Thank you very much for the interesting talk. Do we have any questions? We have time. We have a few minutes. Anyone? I have a curiosity about the sorting. It's just fast for the unsigned integers, or do you also feel in general sorting is quite an efficient operation in Julia?
I think it's especially fast for these 64-bit integers.
But that's just array with 64-bit integers with no other data, or you have a data frame that's sorted based on the column.
So I'm packing in different fields into this 64-bit integer. So the actual position along the sweep axis is quantized to 16 bits. Then there's like a type tag, which is whether it's a point, a line, or a triangle. And then there's a like ID tag that then kind of references a bigger table of other properties.
I see. While we wait for more questions, can the next speaker please come down to set up the audio? No more questions? Let's thank the speaker again for the interesting talk. All right. Our next speaker is Benoit Ricard, and he will be telling us about building a Coulomb explosion simulation on top of differential equations.jl. Please, floor is yours.
Thanks a lot for the thanks a lot for the introduction. So yes, I will tell you all about Coulomb explosion and a bit of about differential equations. So to start without too much additional context, I'm working currently at this place called European X-FIL, which is essentially a very big laser producing X-rays. So that's what it is. James had a longer talks about it. If you are interested, I highly recommend to check it. But in my research group, what we are doing, we are interested in single molecules. So what we do is that we take one single molecules, not so easy, but we take one and we slap it as hard as we can with X-rays. And the way it works is a bit like that. So the molecule is initially doing its things. It's simply chilling around. And then we throw an X-ray at it. And it causes two different effects. The first one is that electrons will be removed. You will actually you can remove up to 2 electrons per atom in average in the current setup. And because the electrons are what keep the molecule together to begin with, what keeps the atoms stuck to each other, once you remove the electrons, the molecule explodes. We call that Coulomb explosion. The molecule will actually dissociate. And what it looks like is something like that. So electrons are removed and the molecule simply falls apart. So this can be realized experimentally, and I have been trying to, or I have been simulating it in order to understand better the experiment, what's going on and what we can learn from it. And I will tell you all about the simulation today. So in the simulation, there is two main parts. There is on one side the electrons, and on the other side the atoms. And we use a fairly standard tricks by separating them because electrons are much lighter than the rest. But also they are the one interacting with the light, which means we have to some extent treat them as a quantum system. But because of some, let's say, technical aspect, we also have to consider them to be a discrete system, not a continuous system. And the reason for that is we are modeling them as this kind of very standard electron structure plots. If you have not seen them before, don't worry. The point is simply that each atoms have a set of electrons bound to them, and you can produce several things that we considered to be instantaneous, so immediate. So one thing you can do at the very right, you absorbed one X-ray photon, you kick out an electron. Very simple and considered instantaneous. Or you can have rearrangement of the electron on a single atom, and you end up ejecting one, for example. Or of course, because you have multiple atoms in a molecule, electrons can move around to some extent. So that's kind of the electron side. It's discrete because you have one state and for all practical purpose, you move to another state without anything in between. And on the other side is kind of the easy part because it's classical physics. It's continuous. It's simply this big core moving around. So because you have removed electron from them, they are positively charged and they mostly interact through the Coulomb interaction. So we have two positive charges, they perch on each other, which is why we call it a Coulomb explosion, because the Coulomb force dominates. And the very nice thing is that there is a package in the differential equation ecosystem that allows to exactly couple discrete with continuous problems. And this is jump processes.gl. So on one hand, you have a discrete system, you have a set of states that are what they are, with some rates to transition from one to the other. On the other side, in the continuous system, you have a differential equation. So this is a general form for a differential equation. And the crucial part, in a sense, to understand how they are linked is that the parameter of the differential equation depends on the state. Here I put a little s for state, which means that when you are in a different state, you actually have a different differential equation. The link goes both ways because in principle, I'm looking at the wrong direction. In principle, on this side, the rates can also depend on the continuous variable like position or velocity, or explicitly on time. But it's, let's say, a smaller difference usually. So once we have that, in principle, we have all the ingredients. We can look a little bit at the implementation. And the way I did it, or the way it is you have to do to use jump processes, is to define these jumps. And here I simply use the Auger Meitner decay as an example. So electron can recombine, in a sense, ejecting one of them. But it works the same for any kind of electronic transition. So here I define one jump, its constant rate, because it do not depend on the continuous variable of the system. And the idea is simply that the rate is to have a jump, sorry, you have to define its rate, how it is like, how likely it is to happen, how fast it happens, and an affect, which is what actually happen when it's time. And there is one per atom per transition type. And the rate is simply the sum of the rate for all possible transition from this specific atom in the current state. And here what I do is that I don't compute the rate in Julia. That's why I asked some question about electronic structure yesterday. I would like to do it, but it's not yet. I did not yet. I've not done it yet. I'm using an external software called Xato. And on you have the sum of the rate, and here I sum them for technical reason. I will go into it in a minute. But basically, when one of the transition happen, what I do is I say, okay, here is all the transition possible. I will just select one of them based on how probable they are. It's very similar to the Gillespie algorithm if you know about it. And then you apply the specific transition you have selected. And the reason why I bundle together all transitions that come from the same atom is simply because it allows to only generate the states that you can reach. If I could decide at the beginning to have one jump per transition, so one jump per initial and final state, but that means I have to generate the list of all possible states at the beginning. And even for an atom of moderate size, it's too big. So I use these things and I just really generate on the fly what's needed. So that's the discrete part. You have the jumps, they can happen. You define when they happen and what happened when they have to be executed. And on the other hand, it's Newton equation. So I'm a physicist. Don't hesitate to ask question about it, but basically it's very standard. You compute the forces. Here it's mostly the Coulomb force. I have added some let's say some genericity to add more forces if you want to. Currently, it's only a harmonic potential to keep the molecule together at the beginning, but I have been thinking about the idea of adding, for example, actual potential, actual molecular bonds to it. But basically, you compute all forces, you add the forces, and then you transform the forces in acceleration, because acceleration is the derivative of velocity, and it's what differential equation wants you to return. And when you have both of them, you have the discrete system, you have the continuous system, you can put them together in a very standard way. You define your differential equation as a standard problem. Here it's second order because it's using equation. You give the acceleration, initial velocity, position, final time. And the last thing here called simulation is just a parameter that keeps track of everything else. So everything in the discrete system in the electrons is in this parameter object called simulation here. And on the other hand, you just have the jumps. So you just put together the jumps in a so-called jump problem with your differential equation problem. And that's it. That's a problem, 3 types of jumps. You have to give coevolve here, which is the way the jumps will be managed, and the dependency graph, which says what you have to update when one of the jumps happen. But it's a technicality, I would say, because at the end you can just put everything together, call solve, and you get hopefully a simulation, one possible trajectory. And I learned a bunch of things doing that. And one of them is that compilation is very long. Compiling this solve call initially took a few minutes. But I then realized that I did two things suboptimally. One of them is that if you don't give a solver explicitly to the solve method, it does some things to try to figure out which one you should use. And it can take quite some time. And the second thing I did wrong is that I initially tried to solve problems that have set an error into them. So it was just failing. So it was taking a very long time to compile and then failing immediately. And I'm not sure why, but it just, once I had removed all the errors, it's actually now compiling something like 30 seconds. So it's very much acceptable. And it's very nice because even if the compilation is a bit long, it's not a problem for me. Because since it's a stochastic problem, we have to repeat the trajectory multiple times to have statistics. So typically I'm simulating, is it going? No. Many trajectories at the same time, usually 10,000, and you have this kind of different possibility of things happening. One of them being that something, as you can see in the top, sometimes the X-ray simply miss the molecule entirely and it doesn't explode. Just so happen. And once you have this statistic, you can actually grab what we can measure in the experiment, which is the escaping velocity of the atoms. And it looks a bit like that. So at the very left, I have the molecule, the experiment, the Julia result, and what I call here XMDIN, which is the reference implementation for these processes. And you can see that they all look fairly similar. So this is velocity in 3D. The main difference is not in performance or anything like that. The main difference between the reference and my implementation is that it's roughly 30 times smaller in terms of code, which is unfair because I'm not doing as much things, but also because I don't count all the implementation done in the package I'm using. The C implementation re-implement everything. I don't. Of course, it's shorter. And for the future, the plan is to use this simulation to actually do imaging. So use the simulation to understand the measurement and then try to get back the structure of the molecule or understand the dynamic in more and more advanced experiment. And that's all I had for today. Thanks a lot.
Thank you so much for this very interesting talk. Questions, please.
So very interesting talk. Well, I was wondering when you do the kind of hybrid simulation, like how do you figure out how often to recalculate the rates? And so I guess, do the rates depend on the positions of the atoms?
No, they don't.
Oh, okay.
There is one that technically does, but we pretend it doesn't.
Okay.
It's one of the approximation. So basically what I do is that when I hit a new state, I compute all the rates to leave it. And then I actually save it to file so that when I run multiple trajectory in parallel, they can reuse it. If it has been used by another trajectory before.
Okay.
Hi, I'm interested in what you said about compilation taking longer if the code had errors. What kind of errors?
A lot of stupid things.
Well, example?
So typically, I put the wrong type in the method definition. There was no.
Oh, so like a method error, for
Yeah,
example.
a method error typically, or I think I had domain error as well. A lot of different things that happen.
Okay.
But the thing, to be fair, I don't blame that on anyone because it's really, I try to put everything together first. And then with the idea, oh, I will fix the error when they appear on screen, which is what I did, but it has this effect somehow to...
Yeah, that's very unusual. I feel like I haven't seen that, but I'm curious what's going on there.
Well, I don't really want to go back to make an MVE.
Yeah, that's fair enough. Yeah, but it's my fault.
Any other questions?
Thank you for the very nice talk. If one wanted to learn something about the excited electronic states of this molecule, would it make sense to do like a double resonance where you pre-excite them with a UV or VUV pulse and then explodes them with the X-ray pulse?
So currently, so yes, in a sense. So we don't get the electronic state of the product ions simply because the traveling time from the interaction region to the detector is like nanoseconds. So I think we have no really any hope for that. What we have been doing pump probe experiment where we trigger molecular dynamics and then probe it at different time. And there is also some, let's say, proposition to measure either the fluorescence or the emitted photoelectron. That could give some information in that kind of setup.
Yeah, I'm sure Benoit will be happy to answer more questions over the coffee break, but let's thank all the speakers of this session again. Yeah, please come back at 3:45. All right, welcome back. Let's start the last session of this afternoon. And let's welcome Fabien Pieck, telling us about random sequential adsorption, modeling adsorbate packing in area selective atomic layer deposition. The floor is yours.
Thank you, Ray, for the kind introduction, and welcome everyone to this talk about one of our modeling approaches to area selective atomic layer deposition. Like to start this talk with a scientific background. So what is actually atomic layer deposition? ALD, in short, is a deposition process where you have two volatile precursors which are sequentially posed in a reaction chamber and react there on a surface and form ideally a thin layer of material every cycle. If you restrict that material deposition to only a certain area of the surface, you call the whole process area selective atomic layer deposition. Here, small molecule inhibitors can be used, and the blocking mechanism is usually following the shown principles. Either the inhibitor molecules can passivate all reactive sites at the substrate surface, or they can prevent precursor adsorption to the reactive sites. In any case, it's for us really important to find inhibitor molecules with a large surface coverage, as that is supporting both of these blocking mechanisms. One approach to model the surface coverage is random sequential adsorption. Here we have a system of interest which is composed of one adsorbate and one surface. The surface is usually in the simulation only represented by its shape, where we use, for example, van der Waals spheres. The surface is modeled by just a grid, where every grid point represents one adsorption or reaction site at the surface. The algorithm then follows very closely also what is called kinetic Monte Carlo simulations. So a random grid point is selected, we put the shape on that grid point, check with overlap or any other shape, and based on that either reject or accept the adsorption. The whole algorithm is not aiming at a very physical model, but it's really just a quick simulation to get like a surface coverage limit of the molecule. In our implementation, we deviated a bit from the standard implementation you can find with Python or R codes in the literature, mainly at 2 points. First, we included also other events than just adsorption, for example, diffusion or rotation events of the adsorbate. And secondly, we used an event list to maintain or keep track of what event is possible so that the whole implementation is rejection free. From a user perspective, using the code is really simple. Currently, we are still working with input files, as that is, I would say, the common approach in quantum chemistry community. In that input file, a lattice is defined by the user. The grid points are defined, and in a very similar way, by using keywords, also as adsorbate, and also which event is allowed is defined. Running the simulation then is really simple. You only need the path to the input file and how often the simulation should be executed. And as a result, we obtain one struct which is containing all results of the calculations and multiple structs with each stored part of the input information. These information are then used in the analysis. Here, our goal was to make it as simple as possible for the user, meaning we defined one function for each plot, animation, or analysis you would like to perform with the data. In the following, I'd like to show you with one example how that looks like. I will again use aniline as an adsorbate and the copper surface as an example for a surface. The first information we can obtain, of course, are these nice pictures where you just see how molecules randomly aligned on a surface. More interestingly, however, is the histogram, which shows you that in the case of aniline, roughly 44% of the surface is covered by the molecule. That means if you have 120-ish adsorbates, you have roughly one adsorbate every square nanometer in that example. Of course, the question is now, is that sufficient to block anything? And there are two implemented possibilities to judge that. One possibility is using what we call effective gap size. Here you place just a circular disk on every grid point, make it as large as possible to without overlapping with any etherbat. And by that, you get a rough statistics, what gap sizes are available and how often. As you can see with the red dotted line, water molecules actually should fit in between, as the radius of water is smaller than available gap sizes. A second approach to judge whether blocking is sufficient or not is to use this result of one simulation and actually use it as an input for the follow-up simulation. In that case, you can, for example, model how water now absorbs on free grid points in between, again, without overlapping with any molecule. What you learn here is, in the set example, that actually quite a large amount of water molecules can still absorb in between. Actually, with 1.4 per square nanometer, we have more water molecules in that example on the surface than blocking molecules. So the question would be, can we improve blocking? And in the beginning, I told you that we implemented several events in addition to absorption events. And so what is the impact of that? In blue, you can see here how it looks like if only absorption events are possible. We have the covered area on the one axis, number of steps in the simulation on the second axis, and you see if only absorption events are possible, the simulation terminates quite early and reaches roughly 44% coverage. If we now allow also diffusion and rotation, you see two important changes. The first change is that you see a slower increase in coverage in the beginning because, of course, diffusion or rotation events do not increase coverage of a surface. Secondly, more importantly, you see that you get a higher coverage on than the 44%. Of course, we can also speed up the whole convergence because we are only interested in the coverage limit, meaning we can, for example, force an absorption event every 25 steps in that example, or we could make absorption events always more likely than diffusion events, for example, which would result in the green line. You can, of course, also combine both approaches, which is shown here with a red line. The important part you should learn here is if we compare now the final coverage we obtain, we see with 55% a way higher coverage than for absorption-only events. However, that comes at a cost, which is also visible here because now we don't run just 160 steps. We now have to run like 2,500 to 3,000 steps in a single simulation. Of course, is that problematic? And the answer to that is no. So here I use the timer outputs package to benchmark my code and to see which part most of the time is actually spent. And two important numbers are highlighted here. One is in red, the time which the code spans in the event list handling, which is roughly 88% of the whole simulation. So if I want to increase performance of the code, I really should focus on that one part of the code. However, what you also see in blue is that a single simulation only takes 240 milliseconds. So that shows you that an RSA simulation is an extremely cheap simulation. So even if you run all the simulations on a single core, it takes you a couple of minutes to run 1,000 simulations. Meaning that method is really nice if you want, for example, to pre-screen several molecules and to judge quickly. It should be suited or interesting for further investigations. With that, I'm at the end of my talk. As usual, you can find the source code on GitHub. And now I thank you for your attention and I'm open for your questions. Thank you.
Thank you very much. Do we have any questions? Well, let me start with one question about the conditions of this absorption process. Quite obviously, coverage is one variable in this whole simulation, but what are the, say, temperature and pressure that's typically involved in this simulations?
So of course, like in the experiment, you usually have very low pressures and temperatures in the range 100 to 200 degrees C. That is common for ALD experiments. Um, However, that simulation neglects all of that. It's really an idealized case. What limit could you expect in case everything is perfect? Of course, in the experiment, it should always be lower than that limit.
Yeah, that makes sense.
Thank you. Thank you for the very interesting talk. Does it make sense to assume a probability that these aniline molecules not only orient like in a parallel fashion to the surface, but that the CH groups are pointing, so to say, downward and form an agnostic bond? And how could this be implemented?
Yeah, yeah. Very good question. So for that simulation, it's important to know how molecules actually align on a surface. And for that, we usually use density functional theory calculations or even MD simulations to get an idea of whether we have one stable structure which is dominating, or as you explained, several conformers. And within that simulation, you can define multiple grids or multiple conformers and also define which should be more likely than the others. And then you will see not just one conformer as shown here in that example, but like just a variety of conformers on the surface.
I have one more question, but can I invite the next speaker to set up first? Is the coverage always limited under one monolayer? Do they stack?
I'm not sure whether I got the question. So the molecules do not stack on top of each other. It's only like that is the important part, that they are not allowed to overlap in the simulation.
So is that a condition you impose, or
Yes.
it's okay? So if you lift this restriction, they will probably stack
Yes.
at the higher coverage.
Yes. So in the experiment, again, maybe to mention that, it's possible that you observe multi-layers of molecules, but usually the process conditions are in a way that molecules rather desorb than form unstable monolayers. And so we restrict the simulation to really a strict monolayer.
Yeah, that makes sense. Do we have any other questions? If not, let's thank the speaker again. The next talk will be a 30-minute long talk by Hugo Utenbosch on modeling optical setups with Beamlet optics.jl. The floor is yours, please.
Thanks for the introduction. My name is Hugo Uitenbosch. I represent my co-authors here today. I'm affiliated with the German Aerospace Center based in Stuttgart, Germany. Oliver Kliebisch is the head of the optical data group where I do my PhD thesis. and Thomas de Corsi is the institute professor. Today I will give a quick, long talk about beam-mapped optics, which started out as a side project for my PhD thesis, but became a useful tool. And I want to present how it might be useful for anyone that works in the laboratory with laser optical setups. So my talk will consist of some sections. Firstly, I want to give a motivation why we built this package and how it might be useful for you. Then I will quickly talk about the optical simulation method that we have implemented. And then I will talk about the package internals. And finally, I will conclude with a quick example and then a summary. So starting off, lasers are very useful for many applications in research and industry. So for instance, here you see a laser communication terminal developed by TESAT that is used for ground-to-orbit satellite communication using free space lasers. You might also do industrial material processing. For instance, here you can see a laser cutting facility, or a system that we develop at our institute, light detection and ranging. So here you can see a satellite laser ranging station that uses pulsed laser in order to determine orbital parameters of satellites in space. And all these systems have in common that you use a laser that propagates through free space rather than fiber-based lasers in order to perform either a useful application like cutting or some form of measurement. And modeling these laser beams combines two interesting aspects of optics. So one part is ray optics. So for instance, you might be interested in tracking the beam axis or how it reflects or is refracted at optical elements. In addition to the wave optical effect of light, which is important if you want to analyze the beam waste propagation and evolution, or simulating interference patterns when multiple lasers overlap, laser beams overlap. So you can see here, for instance, thin disk laser amplifier setup, and all these mirrors need to be aligned, and any kind of disturbance in one mirror will affect the beam path over all other mirrors. In my case specifically, our group researches optical air data systems. So these are technologies which are intended to probe the airstream and the properties of the airstream around an aircraft in flight. So for instance, here you see a laser Doppler anemometer, which is used for contact-free measurements of the airspeed. And commonly, this is done using pitot-static tubes that probe the air pressure, but these are prone to freezing and can cause safety incidents. So we want to investigate optical means because they have the big benefit of integrity, which means that as soon as any part of this measurement system fails, the entire measurement process fails completely and detectable. So this system is considered to be more safe. And this entire technology revolves around for laser beams that are focused outside of the aircraft. So you can perform a standoff measurement of the airspeed outside of the aerodynamic influence of the system. And then light is scattered between aerosols in the atmosphere, which follow the airflow. And then you can measure an optical Doppler shift relative between the aircraft and the airflow. And by performing this measurement with multiple beams, you can reconstruct the airflow vector. And some engineering questions we might want to ask is, how do we need to design the optical elements within the sensor, so lenses and mirrors, in order to achieve some kind of imaging? And also, how do we perform mechanical integration? So you might have a computer assistant design or CAD workflow, and you want to then investigate if it's consistent with the optical model. So in this case, we would ask where do we have our focal point positions, which is quite important for the vector reconstruction, and also peak intensities at those points for eye safety purposes. So there are many already available solutions, commercial as well as open source. And our requirements I've listed on the right side. So for us, we wanted to have a flexible kinematic API and ideally have it be free and open source. So I've highlighted in green some open source solutions that fulfill these requirements, and most notably, I want to highlight OpticSimJL, which is being developed by Brian Günther, and it already implements geometrical ray tracing, so I highly recommend you checking that out. There's also Optiland, which is a Python-based package, and this specific tracing method I want to highlight in the next section is implemented by Brian Cole in Rapier Optics. So now I want to talk about the simulation methods really quick. Classic geometrical ray tracing, I'll give a very crude and fast overview, but basically you have a point in space where you define a ray with a direction and you have an outside refractive index n0 and you assign a wavelength and then you have, for instance, this objective lens group with glass substrates and their refractive indices. So if you want to determine how this light ray would propagate through the optical system, you would determine the surface intersection. At that point, the surface normal, and then apply Snell's law or calculate the reflection. That gives you the next beam direction, and you repeat this process, and you can then calculate the specific path. And if you do this many times, you get basically the optical performance of the system within geometrical optics, which would usually consist of calculating the spot diagram or the point spread function of the system. However, this method assumes that we use plane waves and completely neglects the effects of diffraction. So this method is very fast, but it lacks some capabilities. What if we could use these classical geometrical tracing approaches and apply them to the Gaussian beam, which has some more intricate details? And basically, this is a method which was proposed in 1968 under the name of complex ray tracing. And basically, by tracing 3 rays that represent the optical axis of the beam, the waist and divergence ray, we can reconstruct the Gaussian beam envelope and calculate how it propagates through an optical system. And this method is basically very convenient because we can use all established geometrical ray tracing approaches. However, it assumes locally flat and parabolic surface interactions, and it also assumes rotational symmetry. So it would be very nice to have a formalism that extends this method in order to treat arbitrary and non-rotationally symmetrical systems. And this is a method that was later established in 1986 by Mr. Reynolds, and he added orthogonal pairs of basis rays, which now allow us to trace the astigmatism and on-axis polarization state of our Gaussian beam. This polarization methodology was added by Mr. Walker in 2017. However, there have been many more authors that have extended or implemented this method. So this is great. Now we can track how our beam is influenced by astigmatism, which means that the beam waist is deformed from being circular to being elliptic. However, these individual beamlets can only capture the effect of astigmatism, and higher order effects like spherical aberrations in this case need, for instance, a method called beamlet decomposition. I won't go into detail for this method since we haven't implemented it yet fully, but we can already trace much more complex systems with this approach and use that in order to gauge the optical performance of our laboratory setups. So now I want to talk quickly about how we have implemented this in beamlet optics. So in general, let's assume that you have this free space optical setup. Anyone who has worked with optics in the lab will probably recognize this kind of setup that you need to align. And in general, for our digital representation, we assume that the optical interactions are decoupled from the geometry representation. So we have an optical model of the element you want to represent, but the geometry is decoupled from that, so you can use different approaches like mathematical surface definitions or meshes, or in our case, signed distance functions. And we also assume that elements are closed volumes. Many other packages use surface-based treatment, but we use volume-based treatment. And tracing is performed then sequentially. So I'll quickly show you what that might look like. We use a intersect, interact, repeat loop. So if we define a starting beam, we assign it the position and the direction and the wavelength and the diameter. And then we define elements within our design space, move them into position and rotate them. And then we add all these elements into a system and solve it. So very standard procedure. And if we want to solve the system on the package end, we basically look at the intersection of the beam with all elements and then choose the closest one. And then we propagate the ray or the beam in our case to that point, and then look at the interaction that has been defined. So in this case, it would be reflection. And if we have interactions that are more involved, then we, for instance, can also assume that beam splitting occurs. In our case, that would mean that the beam is split into two parts. So we must also look at bifurcations. And this is also handled in the interaction step. And once we do this, we repeat this for the child beams as well, for this beam splitting example. And that's basically what we call the steady state solution. If you wrap this entire thing into a for loop, we can also do time domain analysis. So if you want to look at the, for instance, mirror oscillations at this mirror, we can then trace how this would affect the rest of the system, which allows us to do other kinds of analysis in regards to mechanical systems. And basically, this allows us to couple optical simulations, in this case, for instance, lens design, element placement, and imaging quality, together with kinematic simulations. So, for instance, this is a turret tracking a drone, and we can look at the effects of, for instance, vibrations, moving optical elements, for instance, for zoom lenses, and in general, optomechanics. I want to quickly talk about geometry representation because we had to put a lot of thought into this. The very first intuition we had was to use tessellation. So basically, piecewise triangular surface approximation. Anyone who has ever used a 3D printer will know the STL format, where you represent surfaces by triangulating them. And you can use this method in order to represent complex geometry very easily. And the intersection calculation algorithms are very fast. However, the issue we ran into is that the normal vector accuracy, which is very important for geometrical ray tracing, is absolutely insufficient. So for instance, if we consider this curved surface, our triangulated surface might have a normal vector that agrees with the curved surface at some point, but already at the edges, we can see that there is a mismatch. And even with interpolation, like is being done in, for instance, Blender, we weren't able to achieve sufficient results. So we decided to opt for signed distance functions. As to my knowledge, this is the first time that signed distance functions have been used in this context. Basically, the signed distance function returns the shortest distance between a point in space and a given volume or surface. The big benefit being that mathematically defined signed distance functions have mathematically exact normal vectors. And this allows basically for any given scene the tracer to ask, okay, what is the minimal safe distance I can propagate? So if we consider this scene and we have this blue cube and this green cylinder, then this sphere, which is calculated by asking all elements to return their signed distance function, can be considered the minimal safe distance. And if we repeat this, then we can propagate our ray through the scene, and this is called the ray marching algorithm, and it's very fast. So this has, as I already mentioned, the benefit of returning very accurate normal vectors, as well as implementing a very fast intersection algorithm. And that's why we basically only use meshes for flat surfaces and placeholder assets, like, for instance, mirror mounts or beam splitter mounts, because they're simply too inaccurate, even for very fine tessellation. And we use signed distance functions for everything else. Our hope is that in the future, Julia will have good support for mathematically defined surfaces. For instance, NURBS.jl as a package we have an eye on, and maybe even have step support, which is a very common file format in computer system design in the future. But for now, we use signed distance functions, and we offer lens constructors or other constructors for all relevant optical elements. So out of the box, we offer optical elements with defined interactions for mirrors, all kinds of lenses, including doublet lenses, as well as beam splitters, and also detectors that allow to capture the effect of, for instance, interference between two Gaussian beams, as well as the more common point split function and spot diagrams. So we're also working on polarizers, which we will release in the future. And now I want to give a quick example of the open Raman spectrometer. This is an open source implementation of the Raman spectroscopy setup. And this type of device is used in order to fingerprint unknown solids or liquids, because when you shine a very strong monochromatic light at the sample, a part of that light is scattered by a process called Raman scattering, and the wavelength is increased, so we have a downshift in frequency. And if we shine a laser light with 533 nanometers, which is green, at the sample, then we will measure the Raman spectrum above 550 nanometers. And all of this setup and the optical design is open source. We can very easily reproduce this. How can I duplicate this screen to that screen? Okay, perfect. Thank you. So basically, for instance, in order to spawn a mirror, we have a defined function, a constructor that returns a mirror, and then we translate it and rotate it, as I mentioned previously. And if we do this, we can also define, for instance, a Gaussian beam in order to trace the laser path and define the optical system consisting of all elements of the Raman spectroscopy setup, and then solve the system for the laser. And then also in the next step, I will show how we can then analyze the scattered light path. But in the first step, we are left with this setup where we can now look at the optical path and, for instance, make some engineering decisions in respect to element placement, also analyze how the rotation of one element might affect the position of the focal point. And in this case, we now have the laser path, and now we would be interested at the focal point position, which is where the scattering will occur. And we can, for instance, obtain all kinds of beam parameters, as I've mentioned previously, now from this ray tracing approach. So we could, for instance, obtain the waist radius or the radius of curvature at that point. I'm only interested in the waist radius, so I will ask basically for this solved laser beam from 100 to 175 millimeters along the optical path to return the parameters. And that will give me the diagram of my beam axis evolution. And then I can see, okay, we have a very small focal spot at around 150 millimeters, which I marked here in the animation. And this is the point where we'll now spawn classic geometrical sources in order to simulate the scattered light. And we can then look at the different colors which we want to separate for our spectroscopy approach using a grating. I've implemented the grating model here. We don't offer a grating model at this point, and I don't think I have enough time to go into the detail, but basically I've only defined this grating model for the geometrical rays, and it implements a very simple diffraction model. But this is how you would implement custom interactions for your setups for models that we don't currently support. But now we can look at the effect of the scattered light passing through our optical system. We have this dichroic mirror that reflects our laser beam, but allows all the scattered light to pass that has been upshifted in wavelength sufficiently. And then we have a long pass filter, which provides additional filtering because we don't want to analyze our laser light, only the scattered light, and the precision window in order to compensate the parallel offset that's been introduced due to the dispersion of these elements. And the achromatic telescope, which is used in order to spread the beam before it hits the reflective grating. This model has been implemented for the purpose of this demonstration, but I will upload it as part of the documentation after JuliaCon. And then we can finally look how we separate our different wavelengths for our spectroscopy setup. And because I couldn't find sufficient information about the objective lens and the camera sensor, I had to replace them with basically a duplicate S-sphere, duplicate doublet lens and detector setup. So the optical performance at this point isn't true to the performance of the ZMAX model. But all of this in total would allow a researcher to design an optical setup for their lab experiment and consider what elements to buy and how to place them and how sensitive they would be to the alignment and vibrations, for instance. So yeah, thank you very much for your attention. Now it's time for questions.
We have quite a lot of time for questions, but yeah, let's thank the speaker again.
Thank you. Yeah, thank you very much for this very interesting talk. I didn't quite understand the meaning of the signed distance function. So in ray tracing, normally you need to know where do you hit a component, and then you need to know what's the normal vector in this position. So I would have thought as long as you know by your triangularization that you hit that component, you can then just say, okay, that is a sphere, let's intersect a ray with the sphere, and you know exactly what you need to know, right? So that would have worked. So but what does it help you to know what's the closest point of that sphere to the origin of the ray?
It basically allows us to implement an intersection approach because the closest safe distance you can travel would bring you closer to that object. So for instance, if you have a sphere directly on the optical axis and you would ask the signed distance function, that distance would be the absolute distance you would need to travel to the surface. So we have hit the target, we can derive our normal vector, mission success. If you now have a more complex object, like for instance a curved surface, the first step of this signed distance function approach would only give you the first iteration needed to reach the surface. So you would repeat this procedure multiple times in order to get closer and closer to the surface. And at some point, your signed distance function return will be 0 if you have an actual intersection. And at that point, you can then calculate the normal vector. So you cannot directly intersect, like with other approaches, a ray with a surface, but you can use this ray marching algorithm in order to calculate the intersection point.
But is it easier to calculate such a signed distance function compared to solving the second order equation of a sphere with a line?
It's very easy to implement. Most of the mathematical exact signed distance functions are only like 2 lines of code. Like they are the signed distance function of a sphere, for instance, is just the distance between the ray point of origin, the sphere point of origin, minus the radius. So these functions are very, very fast. And the main benefit for us was that with this approach, we were able to implement a lot of shapes very easily, which is why we decided to go this path rather than classical surface-based mathematical expressions.
Okay. Can I ask a second question? So normally ray tracing also often includes optimization. Like you want to know certain, like what is the perfect radius of the sphere to get
Yes,
this
yes.
focus and stuff like this. Do you also include that, or have you thought
No,
about that?
we currently do not include optimization capabilities, and I don't think we will for some time, because offering correct optimization capabilities that an engineer could trust is quite the feat, I think. So for the time being, this is up to the user. Defining a system and defining a merit function and optimizing this is possible within the Julia ecosystem, but not our package is not capable to do that out of the box.
Thank you for the very interesting talk. Does it make sense, or is it possible to extend the package to have to include complex refractive indices? Let's say for cases where you have a pump beam that enters a laser rod where it is absorbed.
So currently, the way we handle indices is that we require a function that takes in a scalar input, which is the wavelength, and returns the refractive index, which is a real valued number for most geometrical ray tracing purposes. But from, I think, a programming standpoint, the code should at this point be able to handle complex refractive indices as well. And for our polarization tracing approach, we already need the complex refractive index in order to represent, for instance, coated surfaces like aluminum. So that's totally possible.
Any other questions? I have a quick one. How many lenses, what's, say, the maximum amount of lenses can you put into the system that you can still simulate? The reason I ask is I used to visit the ultra cold atoms quantum labs. The students put in like hundreds of lenses to set up their optical traps and tweezers.
Yeah, for our purposes, I think the maximum we've ever tested was like 17. And you would have, for the non-sequential ray tracing approach, I think n squared increase in runtime. But we use information about previous solutions for the next solution. We call it retracing in order to speed up that process to a linear time.
Right. Thank you. Let's thank Hugo again. Our next talk will be a 15 minutes short talk from Simeon Schaub about modeling repulsion beyond determinants, sampling Pfaffian points processes. Yeah, the floor is yours. Please.
Thank you. I see many people here are excited to learn about these things called Pfaffian point processes. And I'm going to tell you how we can use those to model repulsion and go beyond determinants to this thing called a Pfaffian. really quick, I'm going to go over DPPs. Then I'm going to introduce why we need those Pfeffians, what the heck is a Pfeffian, and I'm finally going to talk about some of our contributions here. For all of you who are interested more in the determinantal point processes, I gave a talk last JuliaCon Local Paris. You're welcome to check that out if you want to learn more about what a determinantal point process is. But basically, this is a thing theoreticians really care a lot about. And you can see here, those are some examples of some very nice pictures you can draw using determinantal point processes. All of those are in some way a determinantal point process. And even like just running this in your Julia REPL will give you a determinantal point process. But why should you care? Well, why do we care about anything today, these days? You can use those for machine learning. So maybe you can use Pfeffian point processes for machine learning. So what is how do DPPs work? Basically, you can imagine how many subsets does the set 1, 2, 3 have? I already spoiled the answer somewhat. It's 8. And what a DPP is, it's a probability distribution over all these subsets. And the probabilities are given by the determinant of a matrix. And you can, for example, for 1 to 3, you take the determinant of the whole matrix. For the other cases, you take some submatrix of our L matrix. And this gives you some factor that is proportional to our probability. Why do we need these Pfeffian point processes? I just told you that determinantal point processes are really nice. Well, I showed you this Julia code. If you run this a bunch of times in your REPL, you can see this is actually a determinantal point process. But we're Julia users, of course. Why do I hardcode complex F64 here? Well, why not just use plain float 64 or even load like quaternions.jl and do it on quaternions? What happens in those cases? And it turns out the answer, you might have guessed it, is Pfeffian point processes. Well, who was this guy called Pfaff? I just wanted to mention a quick fun fact about him. Like 2 of his doctoral students were Carl Friedrich Gauss, might have heard of the guy, and August Mobius, like the famous TÜV guy. Pfeffians occur in the wild. I just mentioned the real or quaternion random matrices. There's also a thing called a random increasing subsequence. And if you take this of a random involution, you can see, for example, this is an involution. Who can find the longest subsequence of this involution? Like it's easy to find 4 or 5. Maybe you can even go higher. So it needs to be increasing from left to right. I'm going to spoil the answer. It's 6 characters long. So you can find subsequences that are strictly increasing, that are 6 characters long. And this is also described by a Pfeffian point process. And if you look at the thing I drew on the left bottom, this is also an example where you have a growth from a corner and you introduce some diagonal symmetry. What the heck is a Pfeffian? So I told you about these Pfeffian point processes, why we'd want them, but what is this thing? Well, you might have taken a linear algebra class and you might have encountered these things on the left. I want to take you through the things on the right, which is usually not taught in your linear algebra class, but it's really quite similar to the things on the left. You have this thing called an eigendecomposition, and in the skew symmetric case, that becomes the so-called Euler decomposition, where you go from like a diagonal matrix to some kind of block diagonal structure with these weird skew symmetric blocks. It's natural to define the determinant from a diagonalized matrix as just the product of all the diagonal entries. and we can define the Pfaffian in a very similar way. So I just talked a lot about Pfaffians and made a big deal about them. But basically, it's the square root of the determinant. It's just a plus or a minus in front of it that really matters. But otherwise, it's just the square root. We can define these things not only on discrete sets or matrices, but we can go to the continuous case. So this is actually this is basically just a matrix, but now in a continuous way, where instead of indices, you now have like a whole real line. And you can see this induces some conditional probabilities, and this diagonal in the middle is basically the repulsion I was promising you in the beginning. So what did we actually contribute here? Very quickly, this is not quite Julia code, but it could very easily be Julia code as well for sampling from such a Pfaffian point process. You basically do a coin flip, and then we have this weird Gaussian elimination step, which is like a skew symmetric version of Gaussian elimination. So instead of like working on single entries, you always work in pairs and like 2 by n and n by 2 matrices. And with that algorithm, which we developed, you can sample from arbitrary Pfaffian point processes. We also looked a bit in what it would take to sample continuous point processes, Pfaffian point processes. There are different ways to do that. You can just discretize the grid. There's this thing called the Arby-Cholesky algorithm, which generalizes to the skew symmetric case. But you can also do your classical Markov chain Monte Carlo methods, and they work quite well. As you can see here, they all more or less converge, except for Gibbs does some weird things because of autocorrelation, but you can solve that issue. What we can also do is we can calculate these Pfaffian kernels. They usually come from some skew-symmetric polynomials. I don't have time to talk about exactly what they are. Come talk to me if you really want to know more about why they are so cool. But you can construct these we can construct these now for arbitrary weights, and we get these really nice kernel pictures. And I thought I just must share these. The red diagonal line is basically they call it the level density. It's basically if you throw all your samples in the same histogram, you get that distribution. We also can do this for the previous one was the real case. This is now the quaternionic case. And you can see there are some interesting things going on. There's really some quite intriguing structure to all this. So why am I talking about this at JuliaCon? Like this is a thing I was thinking about a lot. And if you're here, you probably know all the reasons to use Julia. Like it's quick to prototype, it's really fast. You can run it a bunch of times in a loop, and it'll still be fast. It has all the things we love about multiple dispatch. You have good linear algebra. You have these nice packages, Marquee, Pluto, whatever. No, not whatever. Like it's really great. But what I really care about, it's fun. And I think that's why we should do these kinds of things. And if you want, you can try it yourself.
All right, thank you very much. Yeah, we have 5 minutes for questions. Well, first of all, I want to thank the speaker for actually explaining what a Pfaffian is, because I used to work on the quantum Monte Carlo methods. The one way to go around the non-stochastic Hamiltonian sign problem is to use Pfaffian. I encountered the term multiple times, but I never understood what that is.
Yeah.
So, yeah.
Thank you.
Any questions?
Probably should have prepared some additional nice pictures for these kinds of but maybe we can just look at this again.
Okay, so the question for you is how you embed the Krylov kit into.
Yeah, so I didn't get to talk about that, but it's exactly in how we generate these nice pictures. These are built for you may probably heard of orthogonal polynomials, and there's the skew symmetric analog to this. It's a little bit more complicated because you now have a skew symmetric inner product instead of the nice symmetric one, and those are really quite unusual in some ways. But we developed like a nullity type iteration to get these skew orthogonal polynomials from some arbitrary weight, which is exactly what you see here.
And the eigenvalues came out of Krylov kit exact or.
The eigenvalues you're talking about like the rent and that is really just you can do this in your normal Julia. We did something quite something a little different. We ran this on polynomials. So we orthogonalized skew orthogonalized polynomials against each other.
I see. Thank you. Do we have any other questions?
So what's the process like of getting these Pfaffians for these continuous structures? Like I might have missed it if you explained, but I didn't quite understand how you can, like, is it from solving some PDE that you can derive it from a discretization or?
So your question is how we construct these kernels you see here. So I didn't have time to go through all this, but they are constructed out of these skew orthogonal polynomials, and those get combined. It's basically like an outer product kind of thing, and you fill this kernel, and then we run our algorithm on it.
Okay. Any last minute questions? If not, let's thank Simeon again for the beautiful talk.
Thank you.
All right, it's time for our last and a long talk from Mason Proter about NeuralBox.jl, new features and applications. Please, the floor is yours.
Hi, so I'm Mason, and yeah, so with NeuralBlocks, we are essentially approaching various problems in with brain health and trying to model these things. So as a motivating example, there was a study not very long ago on around 4,000 people with clinical depression, and they found that essentially the entire process of finding an antidepressant which worked for these people was a complete trial and error process. So they started with 4,000 patients, and after giving these patients, prescribing them their first antidepressant, about 63% of them found limited or no relief from their symptoms after their first antidepressant and had to wait 12 weeks before they could start their next antidepressant, at which case, at which point, you know, a lot of them had suffered in the meantime. And by by step 4 of this process of trying to find an antidepressant for these people, only about 123 of the original 4,000 patients were still in the study because most of them had dropped out, not because their symptoms had been relieved by the antidepressants. And for very similar reasons, about 73% of brain targeting drugs, which pharmaceutical companies bring forth for approval, about 73% of these fail at phase 2 of the clinical trials. And the reason that this is happening at phase 2 is that this is the stage where you actually have to demonstrate that your pharmaceutical does anything to improve the patient's symptoms. The earlier stages, you mainly are focused on demonstrating that you're hitting the target that you said you would be hitting. So you plan to target some neuroreceptor and you demonstrate that you hit that target. And you have to demonstrate that the drug is actually tolerable. This isn't going to kill people or something like that. But once you actually have to look at things like improving the symptoms, the entire reason you're developing this drug, about 73% of them fail. And I think one of the only fields of medicine that have a worse rate than this is oncology, so cancer medicine. So part of what's going on here is that depression is not a thing that's located somewhere in the brain. This is a behavior of a extremely complicated dynamical system, and pharmacologists have to find specific transmitters that they think will adjust. You sprinkle some molecule into the brain and then hope that this changes the overall dynamics in a way that is helpful and not psychosis inducing or whatever. But the brain is, as we said, very complicated, and the people developing these drugs are mostly only modeling what their drugs do to a receptor. They are not modeling whole-scale brain dynamics or anything like this. They're very much working on a basis of guess and check. So in various other fields, there's been a long-standing tradition of trying to virtually test before you build a plane or a microchip. You rigorously simulate what you're planning to build before you waste millions or billions of dollars trying to build a plane. And this sort of thing is very much lacking in the brain. So they're mostly only modeling what's going on at a receptor level, not at the brain level. And I mean, it's kind of obvious why. Brains are very complicated. It's very hard to know, okay, what is actually going to happen. Most of their knowledge comes from things like animal trials and various intuitions people have about the brain, because the brain has something like on the order of 100 functional regions, order of 1,000 different cell types, order of 10 to the 11 neurons, and something like 1,000 to 10,000 connections per neuron. And then it's not only just that the brain itself is so complicated and difficult to simulate, but actually forming a model that reduces this complexity is also incredibly difficult, because people don't even agree on what the brain is even doing in the first place. When you want to measure something inside the brain, you have to basically choose what you're going to give up. So you can measure things with good spatial resolution, but you typically give up almost all temporal resolution in your measurements. Or you can measure things with good temporal resolution, but then you basically smear your signal over the entire brain. Oh, okay, I know something was happening in the frontal cortex or something like that. Or you can attach electrodes to a very small patch of brain cells and you can get good temporal and spatial resolution, but you give up any sort of scale. You're just looking at a very tiny patch of the brain. So this makes it very difficult for people to even come up with hypotheses for how the brain is operating. And then there's a further kind of social problem that confounds this, which is that a lot of computational neuroscience is happening on the basis of one-off small models developed by academics. And often these things are kind of, well, it runs on my machine when I choose a step size of this, and then if I change the step size, then my ODE blows up and blah, blah, blah. And these things are non-modular, they're not reproducible by other scientists. It makes it very hard for the field of computational neuroscience to kind of grow. So at Neuroblocks, we've been developing a software product which is trying to address the space of in silico testing of central nervous system models for mostly with a focus on pharmacology. Yeah, so we've been developing a series of models which are all very much related to each other and are derived from each other, which are trying to really, at a circuit level, understand the dynamics of the brain, and or of relevant subsystems, what they're actually doing when when normal behavior is happening, and then model various dysregulations that can happen in disease states, and then measure what a drug might do to that to try and help predict before one of these extremely expensive, laborious, and slow clinical trials actually takes off. Um, so currently we have kind of three models that are on the go, which are related to each other. The oldest and most validated one is this cortical striatal reward circuit. We've done tests on macaques, healthy humans, and ongoing work with bipolar humans. Um, and we'll talk a bit more about this model, but basically it involves the brain trying to categorize different images and getting rewards to learn how the image, what the image does. And this sort of work has a lot of uh, uh, metabolic and aging, dementia, OCD sort of, and other sorts of applications. We have a cortical thalamic circuit, which is more about the audio inputs into the brain and how the brain is interpreting those things, mostly with applications to propofol right now. This is a general anesthetic. So what we do is we give the brain a series of auditory cues like A, B, and then see how the brain responds to this kind of oddball stimulus. This is the B. And then we measure, what our models are doing differently when it's under propofol and when it's not. And then the final one, this is the one that's quite exciting because we're working directly with a pharmacological partner, is basically uh, a sort of anxiety circuit where we're essentially modeling the process of, like, say, you are kind of afraid to go out into an open field, but there's something out in the open field, like some water or some food, and your brain has to negotiate whether its anxiety or its desire to kind of get to some goal is going to win out. And this is very relevant. This is the neuroanatomy that we've inherited from our ancestors that's very relevant for things like generalized anxiety, PTSD, things like this. And we're studying the effects of various drugs on this circuit. And also we have some metabolic work going on where we actually model the effects of metabolism. So we have basically a GUI product that has this kind of uh, very maximalist interface for running and setting up, like these very multi-scale simulations of various different regions of the brain. You can see this AAAB sort of oddball stimulus into the propofol circuit I mentioned before, and then we're measuring local field potentials in the brain, or this is a simulation of what a local field potential measurement might look like. Um, yeah, so this is kind of the software product that we're building for work with clinicians and stuff like that, and also for internal use on the actual sort of modeling tasks that we do internally. Um, so the goal here is to have some sort of thing that can go from the level of receptor dynamics and scale all the way across various scales to behavior and look at interventions on various scales, what they do, what sort of signatures they should have, and what sort of outcomes these things have, and see what various drug targets will do to the brain. The system is kind of made out of what we like to call biomimetic computational primitives. So this is kind of our biological and equivalent of various circuit components. So the brain has a lot of repeated structures that appear in different layers of the brain. One of the ones that we found very interesting and very useful for our modeling is these sort of uh, we call them L-flick or winner-take-all circuits, where you have some sort of inhibitory neuron hooked up to a bunch of excitatory neurons, and based on what these excitatory neurons are doing, whichever one has the strongest output will end up turning off the other excitatory neurons in this sort of lateral inhibition strategy. And this turns out to be very important to information processing in the cortex. And by assembling these things into cortical structures and using similar primitives in other parts of the brain, like the thalamus and stuff like this, they're slightly different structures, but we're able to build actually quite large and rich models of what the brain does. So this is the cortical striatal circuit that I mentioned before, where an image stimulus with some dot pattern is being fed into the visual cortex, and we run this real-time simulation or run a simulation where information flows through all these various circuits that eventually results in a lateral inhibition on a much wider scale that results in some prediction. We can then tell the system whether or not it was correct or incorrect in its prediction um, by giving basically some dopamine to the system. In the actual experiments we did with macaques, this corresponded to some apple juice for the monkeys. In the humans, I think it was something like giving them a couple dollars if they correctly categorize the image. Although the humans are tricky because they learn the dot pattern so fast. Okay, this slide, keep on having trouble with this slide not showing. Okay, yeah, for some reason, yeah, okay, this works. So this just is a little animation of the kind of learning behavior of the macaques in our simulated data. Or no, this is the measured macaques as they learn to correctly or incorrectly categorize these dot patterns. So one thing that's been quite cool about this model, I mean, one can be, you can build a very small classifier that can classify dot patterns. It doesn't mean that it's biologically realistic. But one thing that was quite cool that came out of this is that when we tried to very closely follow what we know about what the brain is doing when it processes information, and we built these circuits. And one thing that kind of came out of the simulations that was quite interesting is that when this circuit gets very good at categorizing these dot patterns, it starts approaching like 90+% accuracy at categorization. Whenever it miscategorizes the dot patterns, there are certain subpopulations that we would see that would routinely get activated before it does the miscategorization. And that was at first we thought it was kind of a weird quirk of the model that it had these subpopulations of wrong neurons that learned to give wrong answers. But what we saw when we went back to do more imaging was that we found these same populations in real healthy brains. And I think the hypothesis is that this is some mechanism to help brains avoid local minima as they learn to categorize things. So if you're not sure if your mental model of some categorization, like, oh, okay, all deer have to have antlers, and then if sometimes you start making some part of your brain pushes you to make a wrong prediction, that can actually help you realize that, oh, I had an incorrect mental model of what I'm seeing. So in order to kind of do these sorts of simulations, we need a lot of things. We need modularity, we need scale, and we need performance. So in order to kind of at least be able to express things like modularity and scale in code, we have a sort of DSL modeling language that is, I mean, very close to various things that Modeling Toolkit is doing, where we are essentially able to symbolically define a bunch of parameters, states, initial conditions, and differential equations. We can do things like events. And then for the kind of multi-scale aspects of this, we can define graphs with members in these graphs. We can talk about connections between objects in the graph, and we can talk about composite structures that have graph substructure in them. So this is that L-flick or winner-take-all circuit that I talked about before, which has an inhibitory neuron here and then a collection of up to n excitatory neurons with some wiring pattern that goes like the inhibitory neuron talks to each of the excitatory neurons, and each of the excitatory neurons talks back to the inhibitory neuron. And these things, anything you can express in this graph language has a kind of visual correlate in our GUI. So we have an upcoming sort of feature where there's an IDE integrated into the GUI, which has this kind of correlation where you can work on the code side and work on the GUI side simultaneously, and they feed back into each other. So modeling toolkit is a very natural candidate for this sort of work. It gives you at least the ability to express scale, and it gives you a lot of performance in small systems, and it's incredibly modular. For our purposes, it didn't end up working out too well because many of the choices that modeling toolkit makes, especially for performance reasons, make it very hard to scale to very large systems with repeated substructure. So essentially, for a lot of the symbolic purposes it needs to create fully unrolled ODE kernels. And this means that you have to recompile everything every time you change anything about the layout of your system. You say, okay, neuron 1 is actually going to talk to neuron 4 instead of neuron 5 or something like this. You're recompiling, and the compile times, this is a graph of the time it takes to the first time it takes to solve a system of all-to-all connected LAF neurons. So there's something like n squared interaction terms in this ODE kernel, and you get this asymptotically n to the 4 scaling of compile times using an MTK kernel. They're doing some things right now actually, which sounds quite exciting for bringing down some of this scaling, but ultimately this sort of strong dependence on the initial system configuration can't work for us with the sort of scale we need for brain simulations. And so we have a essentially graph ODE compiler that we've been writing called Graph Dynamics, which is partially open source. The current version is not yet open source. But this basically allows us to take the structure of the problem that we know about, which is this graph structure, and turn it into an efficient ODE kernel where we only unroll the parts that we actually need to unroll. So the way this is done is we take some graph which has a bunch of nodes and edges in it, and these edges can sometimes be more complicated, like tripartite edges, but for now we'll just talk about bipartite. So we take, say there's a bunch of nodes in this graph of two different types, S and T. We take all the things of type S and we put them into one bucket, and we take all the things of type T and we put them into a second bucket. And this way, you know, if I'm reaching into this bucket, I'm always going to get something of type S. And if I'm reaching into the second bucket, I'm always going to get something of type T. And this lets the compiler make efficient decisions about various things. And then we have to do something very similar but more complicated for the connection matrices, because the connection matrices need to know about the type of the source object and the type of the destination object and the type of the connection that sits between them. And so we have this kind of 3D nested structure of, okay, you have a set of connection matrices for each connection type, and then we partition into a set of sparse arrays for each combination. So S's talking to S's would pull from this sparse array, whereas if an S is talking to a T, it knows it has to pull from this sparse array. And then using that information and unrolling all the type level information. So we kind of MTK style unroll the loop over S and then T, and the loop over this partition, then this partition. But anything inside of one of these buckets or inside of this sparse array is a dynamic loop, and this allows us to get scaling and compile times that don't depend on the system size. They only depend on what types are in the system. So yeah, that's all I'm going to show you today with NeuroBlocks, but just on the horizon, we have version 0.9, which is out right now, and it has this GUI model for creating circuits and testing them. And we have a bunch of interactive tutorials and stuff for using this system. And coming a bit later in the year, we have this new version on the horizon, which will have the IDE integrated. And so you can have interactions between your code and your visual models, which is more useful for circuit designers.
All right, let's thank the speaker first. And we have plenty of time to do some Q&A.
Might be a naive question, but how do you get the data set to train the model?
So
it's like disease specific, right?
so you mean like in this macaque model or?
Any model. You said first three different neurological diseases.
Okay. Yeah. So most of these are not trained like when you say train, we're not doing any sort of deep learning to find the any of the neuron layouts or anything like that or the weights.
Okay.
This is really actually designed based off. We have a bunch of so there are several imaging people or I mean surgeons that we work with who provide us with a lot of information, and then there are a team of computational neuroscientists who delve very deep into the literature to try and learn how these things are wired up together.
So the one we are saying model is not machine learning or deep learning model.
No, we do not. We do not find like these structures and connections don't come from deep learning.
Yeah, it's not a deep learning model. There's a large set of PIs involved with this project actually. So I'm one of the PIs along with Alan Edelman, but then there's a lot of scientific PIs that are actually running labs for this. So for example, we have the lab that is doing work on the macaques. With that is I mean the reason to work with macaques is because they're much easier to give random drugs to than humans, right? But then you could also give random drugs to humans at hospitals and such. So which Charles MGH is involved, the Harvard Medical Center is involved. The Stony Brook Medical Centers. There's a lot of these different things, but then there's also a lot of literature on the functional units, right? So I think about it more like there are circuits, like electrical circuits in the brain, and there is a large literature that has basically been trying to find out how would I model the circuit of this part of the brain, or this part of the brain, or this part of the brain. And so from that literature, now we're saying, okay, a lot of people have mapped out these circuits. We don't know if they're actually correct because there's a lot of shit that gets in the literature, right? But we have labs that are then verifying that certain areas are correct or certain aspects are correct. And then once we've been able to verify out these circuits, and we say, okay, now we have mechanistic circuit models, right? Just like as though it was like an electrical circuit model, and mechanistic models for this piece, this piece, this piece, and now we're building up a complete mechanistic simulation of the brain. And once we have that, then we can do all sorts of predictions that are not relying on like the type of deep learning, right? Because because it's mechanistic, it doesn't have the extrapolation issues that you'd expect from the non-mechanistic, just purely data-driven models.
There are cases where we have neural mass units, which basically are a subunit that's where we only care about average activity of some other brain region. This is usually for peripheral purposes. And some of those, there was a talk earlier in the week that I presented some work that Helmut and Chris and Anthony did on using some deep learning techniques for finding the average equations of some bulk thing of neural mass, but we wouldn't use that sort of technique for the parts that we're actually care about measuring from a pharmacological point of view.
All right. Any other questions?
So you showed that you're still unrolling over the collection of types and types of connections.
Yeah.
Is there any point where it's better for compile time to just do like dynamic dispatch?
For compile time, yes. For runtime, often no. I haven't hit the cases yet where it would benefit from dynamic dispatches, but like for the compile times plus the runtimes, because often when we generate this ODE kernel, we're calling it like tens of thousands of times throughout a simulation, and so we want this kernel to be fast. There can be points where we might benefit from shaving off some heavy compile times, but not losing really an appreciable amount of runtime by introducing some dynamic dispatches high up in this nested structure. But down low in this nested structure, we really rely on type inferred loops.
Yeah, so the innermost loop, like if you think about what the ODE models of these neurons end up being, like the innermost ones, generally the ones that we're going to be making use of are like, 6 to 12, 20 ODEs, right? There are other types of neuron models, right? You can model a neuron as an entire partial differential equation and whatnot. And if you did that, then yeah, then it would make sense to maybe take a dynamic dispatch because, oh, you got like 1,000 equations in there. You're going to eat the specialization time. But if you model the entire partial differential equation of the calcium going down the axon and everything, then you're not going to have a million of them, right? Like, so for this level, for this scale, in fact, it's kind of going in the opposite direction, right? So instead of trying to get every neuron exact, right, you start to say, okay, I have large collections of neurons. So how do I build averages of neurons, right? These are these, next generation neural mass models that was being referenced, right? So, since it's given the scale, the way that we're trying to scale, the innermost models end up being fairly small ODE models. They're very nonlinear, but they're very small. And so you want to then you don't want to take a hit on the dynamic dispatch there because that would be a very strong, that'd be a very large hit in comparison to the size of the ODE.
And just to give some scale on the size of like the amount of heterogeneity we're often running into. So I think the worst case scenario I've seen so far was I think 13 or 14 different node types. So these are neurons, receptors, things like that, stimuli. And then on the order of, I think, 6 or 7 different connection types. So, I mean, this turned into compile times on the order of like a couple minutes, but that's pretty manageable for a simulation that takes hours.
Yeah, I have a follow-up on this. So what is the new, curse of dimensionality? We all know there's no free lunch. Now you eliminate the dependency on the number of neurons, but now
Yeah.
what's the limiting factor here?
Yeah, so if you have as much heterogeneity as you have, like if every member of your graph is of a different type, and if every connection is of a different type, then you're not winning anything over MTK, and in fact, MTK will probably be faster for your purposes. But if you have a lot of repeated substructure, that's when we can benefit a lot from preserving this kind of graph nested structure.
Thank you for the presentation. Part of my question, I'm not an expert in neuroscience,
Me
but
neither.
I'm curious if you could speak to like, is computational neuroscience a compute-bounded problem? Like, how many neurons have you guys been able to simulate through this system? And I'm curious if there are emergent properties that emerge if you know, uh, go through the order of magnitudes.
Yeah, so I think want to be careful. I think the largest we've done for practical purposes had on the order of 1,000 neurons in the simulation, and then something like 10% sparsity. So 1,000 squared times 0.1 would be something on the order of the complexity of the actual ODE kernel. So in this case, it's not, we want to scale up to accelerators and stuff. Like for significantly larger systems, we're very interested in things like GPUs, but we're not currently at a scale where we really benefit all that much from increased parallelism. There are cases where multi-threading could give us some wins, but we're mostly right now sitting in this awkward middle ground where one ODE function eval is expensive enough that the full ODE simulation takes a long time, but the kernel itself is not expensive enough that it's worth parallelizing on a massive parallelism scale. However, I think, yeah, so other computational neuroscientists, especially those using more deep learning approaches, will scale up to much larger systems. But they're that's because they're trying to find the sort of structures that we're basically asserting are there from our understanding of the literature. So for instance, this if you don't know that there's this winner take all L-flick structure inside the cortex, you have to find that using much more neurons and much more connections. And I mean, maybe you can find that with a data-driven approach, but it would be very difficult and would require much more scale than what we're needing.
And one of the things to understand about the project, right, is that the core of the project is to it's to develop new it's to be able to understand the effect of pharmaceuticals, to be able to do, for example, predict new schizophrenia drugs and their effect on subpopulations, right? In order to hit that, we want to get to the highest scale because we want to understand how different brain regions are interacting with each other while keeping the parameters of the mechanistic model, right? We want to, how does this, exact gene affect the calcium signaling on the effect of going to the whole brain, right? And now the way that a lot of groups approached that in the past, like the Virtual Brain Project, they said, okay, let's get millions and millions and millions of neurons, right? Because let's make this exact, right? But there's been a literature that's come along, which is these neural mass models, right? They're saying like, yeah, if you have a million of the same neuron and they're connected in a given way, here's an approximation to that behavior, and you go, cool. Like, and now if you have so some different sparsity patterns, now maybe you don't have a neural mass model that's known, but we can use scientific machine learning to find that. And because of that, we have ways to get up to scale. So what we're trying to do with the project is not necessarily to make the biggest model that has the most neurons. That's something that people have been trying to do before. It's not necessarily the way to get to the most useful brain. Instead, what we're looking for is how do we get to a version of the brain that is as accurate as possible while getting the entire scale and keeping all the ways to be able to do pharmacological interventions.
And I think one thing to appreciate here is that, like, the actual scale of the real brain is so, like, even someone who has 10,000 times more neurons than what we're simulating is still closer to the scales that we're working at than they are to the scales of the actual brain. And so if you get yourself 3 orders of magnitude or something, you're not actually necessarily getting any qualitatively closer to the sort of scales that are actually happening at the brain. And so you really need to build models which are informed by the relevant dynamics of the brain that are not trying to exactly replicate everything that's happening in it.
All right, let's thank Mason and other speakers of this session again. And I also want to give a shout out to our AV team who stayed with us in the whole day. Thank you so much. And please make your way to the tent for the State of Julia keynote and the closing ceremony. Thank you very much.